You're live now? Okay. You're all set on this planet gets out the water.
Yeah. Which might, yes. Is this too bright here? Feels too bright.
How do we do that? Because
No, you might.
thank you so much.
Good, how are you?
This is okay.
Is it better now?
Yeah, it's better.
Can we check?
Thanks.
I don't know what check.
No. Always learning.
Thank you so much.
Is all good online? You can hear me? Okay. How about now? Okay. Okay, let's get started. We're at lecture 20 today. Getting closer to the end, huh? Of the semester. Hopefully you guys are having fun. Today we're going to finish up prefetching. We're going to talk about an important aspect of prefetching, which is execution-driven prefetching. And then we're going to start multiprocessors. Hopefully it'll be fun. This execution-based prefetching, as I mentioned, prefetching is an area that I've been working on for 25 plus years. It's a very exciting area. There's still a lot more to do in this area. And execution-based prefetching actually has something even closer to my heart because it's an area where I did my PhD in. So we'll talk about some of that work as well. Okay, but before we get started, this is your reminder on potentially submitting to the data prefetching championship. Where's Rahul? He's not here. Genome is helping Rahul though with the championship. But if you have questions, you can direct them to Rahul or Genome. Genome can convey them to Rahul if he doesn't know the answer. And this is open to everyone across the world who has good ideas. And it's a championship, meaning there is some evaluation criteria. You submit a prefetcher based on some constraints, and they will be evaluated on the infrastructure that you're going to use for Lab 4. And then you may win the championship based on some metrics, performance metrics, essentially. Okay, so, and if you do Lab 4, you'll get a head start, actually, because it's essentially what you will be doing for the championship. But you may need to think a little bit more out of the box for the championship, because what we ask you in Lab 4 is implementing known ideas and maybe exercising some of your new ideas. Does that sound good? Okay, good. So this is a slide that you've seen before. We covered actually software prefetching, hardware prefetching. Today, we're going to talk about execution-based prefetchers. But just to jog your memory, we've covered a lot, actually. We've covered stride prefetching, stream prefetching. We've covered example prefetchers that are actually employed in industry, of which there are many. We've covered memory region-based stride prefetching. This is the seminal paper by Juppi from 1990. We've covered locality-based prefetchers. And we also covered feedback-directed prefetching, which are covered in the same paper that we wrote in 2007. And we did discuss briefly multi-core issues in prefetching, bandwidth efficiency, coordinating the control of multiple different prefetchers. We didn't discuss some of the other things, but we don't have time to discuss. But essentially, you can make information about prefetch accuracy available to the memory controller as well to do better memory scheduling. For example, if you have a memory controller that is trying to decide between a prefetch versus a demand request, and the prefetch is accessing a row that's open, and the demand is accessing a row that's not open, you may actually want to prioritize the prefetch request over the demand request if the prefetch is highly accurate. That way you exploit the row buffer locality. You don't waste it by switching to the demand, because the prefetch is going to be very likely useful, assuming the accuracy of the prefetcher is very good. On the other hand, if the accuracy of the prefetcher is not very good, then you may decide, okay, you may even decide to drop the prefetch at that point if you have a lot of contention for bandwidth at the memory controller level. So this paper talks about some ideas like that, and these ideas are actually quite beneficial in real processors to save bandwidth or intelligently schedule requests such that you don't waste bandwidth at least. Okay, there are more ideas, but we don't have time to cover them. These are just for your reference. We also talked about more advanced ideas on using machine learning to decide what to prefetch, or using machine learning to formulate the prefetching problem. We talked about Pythia, for example. We also referenced this book that I would definitely recommend to anyone who's interested. I read the first edition of the book multiple times, I think, when I was first working on reinforcement learning for memory controllers. The second edition is even better and has more applications, as you can see, that are not actually in the first edition. Okay, and we talked about off-chip load prediction, essentially predicting whether a memory request that is generated by the core is going to hit on the on-chip caches or will access the off-chip memory. And this is useful because you can start the request early without accessing the cache hierarchy before you start the main memory request if the memory access is going to go off-chip. And we also talked briefly about specialized prefetchers for targeted workloads. I'm not going to cover them in detail right now, and that brought us to execution-based prefetching. That's kind of a summary of 1.5 lectures that we've been through so far. Sounds good? Any questions on those lectures so far? Okay, everything's good. Okay, let's talk about execution-based prefetching. This is actually a very nice idea. It could be done in software or hardware, but the basic idea is very simple. Pre-execute means early execute early a piece of the program solely for prefetching data. This piece could be a pruned piece, meaning a smaller piece, not the exact program. But it could be also the same program. But you may need to be very careful about what to execute and what not to execute in the same program. If you want to execute a pruned or smaller piece of the program, you need to, the goal of this pre-execution is to prefetch for the main program, right? Main program is going to have a load, and you want to execute something that, execute a piece of the code that actually leads to that cache miss. So you want to eliminate the cache misses, that's your goal. So you want to identify pieces of code that actually generate cache misses and execute only them. If a part of the program doesn't generate cache misses, you don't need to execute it early, right? Because our goal is to actually prefetch for the cache miss such that that cache miss is not incurred by the program. That's the idea. I'm going to give you a picture that explains it in a nicer way. So this pre-executed piece of the program, it can be considered a thread. It is actually in general a thread. It has its own context, but it's a speculative thread, meaning it's not visible. Its results are not usually are not visible to the architectural state. And the speculative thread can be executed in many places potentially. It could be executed on a separate processor or core, on a separate hardware thread context, like in multi-threading, for example, or on the same thread context in idle cycles, meaning same processor. You just kick out the main program and use the speculative thread and execute it, and then you kick in the main program back during cache misses. We're going to look at all of these options actually. Of course, there are many questions over here. How do you construct the speculative thread whose goal is to prefetch for the main program? You could do all of these in software, hardware, or cooperatively, or you use the original program. So software-based pruning means you prune using compiler, for example, or using programmer knowledge by hand coding. You find which instructions lead to cache misses, and you only create a thread that executes. And you have a spawn or fork instruction that spawns or forks the speculative thread at the right moment, such that while the speculative thread is executing, the main program is also executing. And when the main program reaches the cache miss, the speculative thread already prefetched the data. That's the idea. You could do this purely in hardware. Of course, it'll be more hardware intensive, but there are proposals like that. Or you could use the original program, like what we're going to see, which is what I did in my PhD thesis, for example. You don't need to construct a new thread. Original program can be used as a thread itself, but you ignore some instructions, execute it much faster. Because it's speculative, you don't need to worry about correctness, essentially. And we'll see that. So the speculative thread, the key idea is to discover misses before the main program reaches a cache miss. Right? And to be able to do that, it needs to execute much faster than the main program. Right? Otherwise, I would execute the main program. And for this to execute much faster than the main program, you need to avoid waiting or stalling as much as possible. And you want to compute as little as possible. As long as you execute just enough code to get to the cache miss that's going to be produced by the main program, that's enough, right? You don't need to get correct results at all. Makes sense? Because the goal is to just uncover that cache miss and prefetch it into the cache early. Okay? So to get ahead of the main thread, you can actually do a lot of pruning. You can perform only address generation computation, maybe some branch prediction, because if a branch prediction actually determines your address generation, which address will be generated, that could be important. But if the branch is very predictable, then maybe you don't need to actually do branches. You don't need to execute branches. And maybe you want to do value prediction so that if there's an unknown value somewhere, you predict it such that you hopefully correctly execute it. These are actually a lot of ideas that are employed in any kind of execution-based prefetching. And as I said already, this is purely speculative, so there's no need to recover the main program if the speculative thread is incorrect. Meaning, what does incorrect mean in this case? Basically, it can generate some garbage address, right? It's okay. It will basically get maybe it will generate an exception, but you don't care about that exception because it's purely speculative anyway. You don't even handle the exception. Yes?
Is this exactly same as Runahead execution?
Yes, we're going to get to that basically. Runahead execution is a form of execution-based prefetching. So yes, the answer is yes, but Runahead execution makes some choices. And you can, of course, enhance Runahead to actually make different choices. Okay. Yeah, exactly. Runahead execution is a form of execution-based prefetching, but execution-based prefetching is more general than Runahead execution. Okay, we'll see Runahead execution in detail because that's my thesis. And because it's implemented in real processors and it's inspired a lot of work also. So, okay, so that's a very good question. Okay, so this is actually a very nice picture from the Ziliso and Soy paper from ISCA 2001 that basically summarizes the issue. And this thread-based pre-execution is a very general idea. It doesn't need to be just for prefetching, as you can see over here. But let's take a look at the prefetching part. So you have a main program over here, and you fork some speculative thread. This is the speculative thread, basically. It executes a small piece of the program such that it generates the cache miss. Cache miss is serviced. And by the time the main thread gets to the load, it's in the cache, right? So this way you overlap the latency of the execution of the main program with the cache miss. Makes sense, right? You just need to be able to execute this thread concurrently with the main program at some point. Right? And then you get a speed up, basically. The general idea is applicable to other, let's say, performance degrading instructions like branches, for example. You could actually have a speculative thread whose purpose is to calculate the branch target address and the branch direction before the main program gets to that branch. When the main program fetches that branch, you have that information ready, and you basically change the target address to the predicted target address from the speculative thread. This way, you can be much more accurate than your branch predictor that may not have enough information because you're really computing what the main program hopefully would do. It may not be perfectly accurate, but hopefully you'll be more accurate than a branch predictor. That's the idea, basically. And I like this picture over here. And this idea has been around since 1990s. And this is actually one of the first incarnations of the idea. It's a technical report by Michel Dubois, assisted execution. And this is one of the first papers, simultaneous subordinate microthreading. And I recommend you take a look at it. Okay, so there are many issues in pre-execution, of course, right? Thread-based. Where do you execute the pre-computation thread? When do you start it? When do you terminate it? Where to execute? There are trade-offs over here. I don't want to cover all of the trade-offs, but if you actually execute on a separate core, you don't contend with the main thread, right? You don't slow down the main thread. That's good. But you may not prefetch into the same cache. at least the first level cache, because the cores may have private caches, right? You prefetch into this shared cache between the cores, right? So you may not cover all of the latency. If you execute the pre-computation thread in a separate thread context in a multi-threaded processor on the same core, you cause more contention to the main thread because you're sharing the pipeline, the execution of both threads on the pipeline, but you prefetch into the L1 cache, which is shared by threads that are executing on the same core, almost always. Or you can actually be a little bit more aggressive. You can do it on the same core, same context, meaning you don't even need a multi-threaded processor. You have only one single-threaded, single-core processor. And when the main thread is stalled for some reason, maybe it gets a cache miss, you switch in the speculative thread, and the speculative thread executes for some time, prefetches for the main thread, and when the main thread cache miss returns, you go back to the main thread. Now, clearly, this is frugal, meaning you don't waste a lot of hardware. You don't need to use another context, which may be used by some other application. But you may not run ahead, let's say, execute ahead much longer because you're switching when the main thread is not stalled, or you're basically executing the speculative thread only when the main thread is stalled. But you're also bringing data into the same caches, and you can be training some of the structures, as we will see in run-ahead execution. So people have done all of these basically in real life. In fact, if you can actually write a speculative thread yourself and execute on a separate core. It doesn't even need to be speculative, by the way. It can be actually architectural. You just need to use prefetch instructions yourself. Right? So you can actually, as a programmer, do this yourself. You just need to know what you're doing. Okay, so when do you start the pre-computation thread? You can insert some instructions well before the problem load. Problem load means a load that's going to cause a cache miss. How do you determine those? Based on profiling or some program analysis like we discussed last time. These are all so-called delinquent loads, basically. They don't behave nicely. They actually miss the caches. The question is, where do you insert this spawn or fork instruction? This determines the timeliness, essentially. So if you go back to this picture, if your fork instruction was, for example, right before the load, you're not going to save a lot of latency of the cache miss. If your fork instruction is way too early in the program, you may not even get to the load because you may have a lot of control flow that takes your program somewhere, and that load is never needed, for example, right? So you just need to place the fork at the right level, the right place. And that's actually, again, timeliness issue. And we already discussed this. If you do it too late, too early, neither of this good. Ideally, you would like to do it just at the right time. Or you can do it when the main thread is stalled, as we will see with the run-ahead execution. When do you terminate the pre-computation thread? Again, this is the question is, what is that thread? What does it do? And does it do a lot of work? You can have some cancel instructions when the thread goes on some path, for example, you may cancel. Or you may have effectiveness or contention feedback like we did with prefetch throttling, right? This thread has not been very good in the past, so I'm not going to expect it to be good, so I'm going to not even start it. You could also do that throttling, for example. There's another issue, which is when do you start the computation thread? Does a speculative thread generate another speculative thread, right? Because while you're executing the speculative thread, you may actually have a fork instruction if you're actually looping, for example. In that case, again, that's a design choice, right? That's what is the depth of execution in speculative threading? Yeah, hopefully these are very interesting issues. It has been very interesting for many people. Many people have written papers about it. This is one of the seminal papers from CK Look at Intel. And essentially, he proposed a mechanism for software-controlled pre-execution on SMT, or simultaneous multi-threaded processors. And there are many issues in software-based pre-execution discussed in this paper. I would recommend it. It'll be part of your reading assignments. But you can see these are pictorial examples. So if you're, for example, you have multiple pointer chains, and you're going to potentially do different pointer chasing across different linked lists. You may be doing this if you're actually doing, for example, hash table queries, right? You have query one that goes to one bucket in the hash table. There's a linked list. That may be your main program. While you're doing that, speculatively, you go to the next hash table access, which maps to some other bucket in the hash table, and you traverse that concurrently with a speculative thread. And maybe you can actually have 3 speculative threads pre-executing different hash table queries by traversing the linked lists in different buckets, right? I like this example because that is nice. Another example is basically array access, which is essentially the same. While you're traversing this array, you may traverse the other arrays concurrently. Or you may do multiple procedure calls while you're executing this function. You speculatively execute some other functions in the program by speculatively launching them. Makes sense, right? And by the time you get to, for example, bar, you already prefetch the data into the caches. That's the idea. Or by the time you get to this hash table query, you already prefetch the data into the caches. That's always the expectation and hope. Or you could actually do multiple control flow paths. For example, you have a branch, if then else over here. While you're executing this part, you may actually start pre-execution of later parts of the program. And by the time you get to any of these, hopefully you prefetch the data that will be touched by those parts of the program. So you can see that there are different ways of doing it, and different program structures may lead you to be less or more accurate. Of course, when you actually start a speculative thread, you need to figure out whether the data values are available, right? Because this foo function may generate some input values for this bar function. And if you don't know those data values, and if those data values lead to an address that's going to, or some sort of address calculation computation that's going to miss in the cache, you will not get it correct unless you maybe predict the value, right? So it's good to think about these issues that you may need to cover. Okay, so this paper has a nice example. I will not go through the entire example. I'll let you study it a little bit, but essentially it shows how to speculatively parallelize meaning for prefetching purposes, a program that's used for vehicle scheduling. It's a very famous benchmark from Spec 2000 suite, MCF. It's very memory intensive, actually. And essentially what this benchmark does is it goes through, this is actually one of the main loops. You traverse the list starting with the first node that's just assigned over here. And you can see that this is doing pointer chasing, right? So what this paper does is it essentially, before you start the first iteration of the loop, you add an instruction, pre-execute start, and there's ISA support, instructions and architecture support, that's proposed in this paper. You add this instruction, pre-execute start, and this is the program counter where the pre-execution will start, end4. End4 is after this whole loop, as you can see. So this loop is executed multiple times, and then you go back and execute it again, right? For each trip, you execute it. So while the main program is executing this while loop, the speculative program will start at the end of it. So it will go back and execute another instance of that while loop, speculatively, okay? So it will basically execute another trip or whatever it's, another trip, basically, next trip. Make sense? So here you're parallelizing across the execution of these loops. One execution is non-speculative main thread. The next execution will be by the speculative thread, okay? And then they have a pre-execute stop instruction, meaning that a pre-execution thread that's executing speculatively an iteration of the loop will not generate, will not go to the next iteration, basically. Hopefully that makes sense, yeah. Okay. And also they say that notice that any pre-execute start instructions encountered during pre-execution are simply ignored, as we do not allow nested pre-execution in order to keep our design simple. Okay, there could be design choices. That's one design choice they made. You can study this on your own. At some point, if for example, the pre-execution thread, this is the last iteration of this for loop over here. If the thread has reached the end of that iteration, there's a pre-execute stop instruction over here also. Basically, you explicitly stop the pre-execution threads. These are some ISA extensions that are proposed in this paper. Pre-execute start basically says, it requests an idle context to start pre-execution at a start program counter and stop it when maximum instructions have been executed. This may be an optional argument. And thread ID holds either the identity of the pre-execution thread or -1 if there's no idle context. So you can see that if there's no hardware context that's available, you don't start the pre-execution. And you can actually do something based on that, because thread ID is a software construct that you can branch on, right? Okay, this instruction has effect only if it's executed by the main thread. As you can see, speculative threads ignore this instruction. Pre-execute stop, I think that's very clear. pre-execute cancel, essentially, this is done by the main thread, I think. Terminate the pre-execution thread with thread ID. Yeah, this instruction has effect only if it's executed by the main thread. So you can see that this is software controlled. A programmer or a compiler can use these instructions to optimize the program and generate pre-execution threads that are effective. Now, if you look over here, the pre-execution thread is the main program, right? But this doesn't have to be the case. Here, the pre-execution thread is doing the same thing as the main program, but maybe potentially you could actually direct the pre-execution thread to some other program counter that's actually a pruned part, right? So it's perfectly possible. They don't do it over here, but it's possible to actually have a single binary and execute another part of the binary that's a pruned part of the main program that's essentially doesn't execute the exact same code as the main program. Okay, so these are some results that they report at the time. And you can see that most of the time they gain significant performance improvement. This is the MST workload minimum spanning tree that we have seen in the past when we looked at the content direct prefetching, if you remember yesterday. You can see that there's significant performance benefit, but sometimes they don't get performance benefit. Actually, they lose performance, about 5% over here. This is execution time. Higher is worse, lower is better. And you can, and the reason is there's contention that happens with the main thread. And also it seems like this particular program doesn't have a lot of cache misses that it stalls on. The black parts actually load L2 miss stall, and this black part is relatively small, as you can see here. So okay, so this is it could be optimized also. Maybe they don't have very optimized mechanisms for stopping pre-execution throttling, and certainly they don't in this particular paper, I know. Sounds good? Any questions? Yes.
Is it sometimes an issue that you get coherence problems because with the data, because the speculative part already manipulates data possibly, which then the main thread needs to be unmanipulated?
Yeah. Yeah, so that's a very good question, basically. Normally, the speculative thread may manipulate data, but that should not be visible to the main thread. So in this paper, we didn't discuss it, but it should not manipulate data that is touched by it, because this is purely speculative. So you need some special structures in software or hardware to make sure that that data doesn't get manipulated, doesn't get changed in the main thread. So normally, you don't have coherence problems because you're speculatively doing the speculative. Make sense? But if you were not doing the speculative, you're absolutely right. You would have coherence problems. So if you do some wrong thing over here, you would actually have coherence problems. Very good question. We'll cover coherence more next time. Any other questions? Okay. So this is another paper that actually these two papers are actually very nice papers. These are from Craig Zillis's PhD thesis. He did work a lot on this speculative execution for prefetching, especially, or in branch prediction paradigms. And you can see over here that this is a virtual place and route program that's used at the time for processor design, let's say. And you can see that this program does something, another while loop over here. And they analyze the code and they figure out that there are some performance degrading instructions. And this happens to be usually a cache miss. And this happens to be usually a branch misprediction, that comparison. And in this paper, they describe how to actually generate speculative threads by pruning the program. That's called speculative slices or backward slices of performance degrading instructions. So if you identify this to be a performance degrading instruction, you can analyze your program and figure out which instructions in your program lead to the computation of this address. Right? And then you basically execute only that set of instructions to compute that cache miss. Similarly, you can identify which instructions in your program lead to the correct computation of this predicate evaluation. You're comparing some cost to another cost, as you can see, from cost to the I from cost to I to cost. You just execute that part of the program that leads to the evaluation of that predicate. Hopefully that makes sense. And then you need to, once you do that, I'm going to show you in the next slide, you need to decide where that speculative thread that contains all of those speculative instructions can be launched. And you can see that they actually have a fork point that they add. And you can see that this is the add to heap function, where the performance degrading instructions are in the add to heap function. They start the speculative thread much earlier So there's an allocate heap data function. There's some other stuff over here, and eventually add to heap function. Though they raise the fork point to much early in the program. And at that fork point, some speculative thread is called, and this is what the speculative thread looks like. This is alpha assembly for the full function, add to heap function. Again, you don't need to go through it over here, but I'll read it, I guess. The instructions are annotated with the number of the line in figure 2. Figure 2 is not here. The problem instructions are in bold, and the shaded instructions comprise the unoptimized slice. So bold instructions is floating point, branch and equal, and this load instruction. So these are the problem instructions, and the bold instructions are the instructions that lead to the computation of the values or the results of these problem instructions. So if you don't optimize, you need to include all of these shaded instructions. Sorry, did I say bold? Shaded instructions are the backward slice. But they go and optimize. I think they hand optimize and do some tricks over here. And this is the slice in the end. So this is the backward slice that is optimized. And these are the 2 instructions over here. So they do a lot of optimizations, and they need to predict some things over here. Live in, for example, needs to be predicted. But you can read the paper for more detail. The key takeaway is your backward slice may actually contain a lot of instructions that the main thread already executes. But if you go ahead and optimize it, you can create a speculative thread that's actually much faster, that doesn't need to execute as many instructions as the main thread. That's the key idea. And you need to do that, otherwise your speculative thread cannot go fast, right? And the goal is to make the speculative thread go fast. For more detail, definitely take a look at this paper. It's a beautiful paper. Any questions? Okay, this paper describes how to do this by hand. There's also work that describes how to do this in hardware, purely in hardware, purely by compiler. So there's all sorts of work over the course of like 30 plus years that discuss how to construct this thread, for example, when to schedule it, where to add it. As a programmer, you can see that it's not easy, right? You need to know exactly what's going on. People have developed compilation passes to do this, and people have developed hardware support to do this. In hardware, actually, you can do all of these optimizations, but then hardware becomes expensive. Okay, now we're going to talk about an execution-based prefetcher. Okay, right ahead. Yes.
The previous slide, it was speculative thread. Like if the loads in the speculative thread are dependent on the loads that the main thread is doing.
Yes.
Then it is always a hard deadlock, right?
Yeah. So basically, yeah, you need to make sure that the speculative thread is scheduled at the right point, such that you have the values or you predict those values, right? Yeah, you need to minimize the dependencies between the main thread and the speculative thread. Or you need to recompute some of the things this main thread is doing, such that the speculative thread doesn't depend on the main thread.
Okay, so you're saying we do some prediction over here.
Exactly, yeah. Yeah, the key is basically running these as separately as possible. Yes.
So basically, we have this one original loop, and we are slicing that loop into another smaller loop, which is prefetching things for the iterations that are coming next.
Exactly. You can think of it that way. Yeah.
So we also need to have a cleanup loop, right? Because some part of the computation, which is there in the last tail of the data, which was brought in speculatively, we need to have another compute part for that reason.
Not necessarily, because this is all speculative, remember. We're not changing the architectural state. We're just prefetching stuff into the caches or some hardware structure to feed the branch predictor. We're not changing the data values the program is supposed to touch. This is very similar to the earlier question with coherence, even though it's not related to coherence. The key realization is that this is completely speculative. Whatever you do in the speculative thread is not going to affect correctness. Okay? Yes?
And where do we store these speculatively fetched data? Like
in the caches, essentially. Yeah.
But then what he said, then we'll have a coherence problem. So do we have a reserved space or something like that?
No, you don't have a coherence problem because you're not updating the data. Right? You're reading the data.
Okay,
you cannot write to the data. If you write to the data, then you're doing something wrong. But if you read the data and bring it into the caches, that's very similar to what we do with prefetching, right? Yeah. Okay. The key happens when you update a register, update a data value, and you never do that with the speculative thread. Okay. The question is, how do you actually update? How do you handle updates? Basically, you try to do no updates. If you look over here, there are no stores over here, right? You try to get rid of stores as much as possible. Sometimes you may not be able to get rid of stores because stores lead to address computations that are going to load a cache block. But then you need to handle that store specially. You store to a scratchpad location, and you change the addresses such that store and load communicate, but you don't change the load address. So you can play a lot of tricks to make sure the speculative thread doesn't update the architectural state of the main thread. Okay. Okay. So now let's talk about how to make this as simple as possible, maybe. I think this is one of the simpler ideas. That's why it has had a lot of impact. So I'm going to talk about Runahead execution, which is an execution-based prefetcher. And this is what I worked on for my PhD thesis. This is the first paper that I wrote in HPCA 2003. It's essentially a technique to obtain the memory level parallelism benefits of a large instruction window. I'm going to explain this a little bit more. So what happens is, if you have an out-of-order execution processor, you have an instruction window, and at some point you stop fetching instructions to the instruction window because your buffer is full. And if your buffer is full, and if it's because of a long latency cache miss, because you're waiting for data, Runahead execution says, checkpoint the architectural state at this point, meaning registers, and enter a speculative execution mode, very similar to speculative threading, like we discussed, where the goal is to speculatively execute the instructions of the main thread with minimal stalling. Remember, we took a checkpoint, so we're going to get back to that checkpoint at the end of this Runahead mode. You speculatively pre-execute the instructions with minimal stalling, meaning you can ignore some instructions, because again, we're not going to update the architectural state with this. We're not going to change any data values. Okay? You can ignore a lot of things. The purpose is to solely generate prefetches for instructions that you're going to execute later in the normal mode. If you have a long latency instruction, it could be a cache miss. You mark the result as invalid, or you predict the value and drop the instruction. It could be another long latency instruction, a floating point operation, for example. I'm not going to execute the floating point operation. I'm going to mark the result invalid. I'm not going to trust the result, right? Or you predict the result value and then drop the instruction. This enables room for later instructions in the window, meaning you could keep processing instructions because you clear the processor from instructions that you cannot execute for some reason. When the original cache miss that caused entry into this mode returns, basically you restore the checkpoint, copy the registers that you checkpointed at the beginning to the main register file. You flush the pipeline and you restart normal execution from the checkpoint, the program counter that caused entry into this Runahead mode. Hopefully that makes sense. Let me give you an example. Ideally, what you want is perfect caches, right? You compute, all of the loads hit, and the processor is happy, it never stalls. This is ideally what we want. But with a small instruction window, out-of-order execution processor, what happens is you get a cache miss. Soon after that cache miss, your window becomes full because you cannot finish this cache miss, you cannot complete it because the result is not ready. You may not be able to execute some of the instructions, that's fine, but it doesn't matter. You cannot retire any of the later instructions. And with a small instruction window size, at some point you stall. And the processor stalls for a long time because memory latency is long. After some point, the cache miss returns from memory and the processor can continue execution. Right? But soon after that, in a memory-intensive program, as we have seen, you get another cache miss and the processor stalls again. So this is why processors wait for a long time, right? Most of the time they're stalling. Now, in a Runahead execution processor, the idea is you compute for a while, you get this cache miss again. Soon after some point, this cache miss becomes the oldest instruction in the window. So you have a clean place to take a checkpoint, right? Because no instruction after this cache miss finished, this cache miss did not finish, and every instruction before it has finished. You have a place to take a checkpoint, and you checkpoint the register file as it is at that point. You checkpoint the program counter, whatever architectural state you may have, special registers, etc. Not the memory, because memory we're not going to update during the speculative mode. And you enter a processing mode where you execute very fast, meaning you ignore the value that is not available because of the cache miss and drop the instruction that caused entry to this Runahead mode. And you ignore all of the values that are dependent on the cache miss, basically. Or you predict the value, that's another possibility. And the goal is to execute as fast as possible without stalling in this Runahead mode speculatively, such that you get to the second load miss. assuming it's independent of the first load miss. And you start executing that load miss in memory, and that gets serviced in parallel with miss 1. Soon, at some point, this one completes. You flush the pipeline, exit this run-ahead mode, and restart execution from the load 1 that caused entry into run-ahead mode. It hits in the cache because it's serviced. And at some point, miss 2 also completes. And when the processor actually gets to load 2, it hits in the cache. So this way you saved the second stall. Because what you did is, instead of stalling for the first one, you did some work. And that work was completely speculative. The goal of the work was to actually uncover later cache misses that may come up later in the program. Make sense? So it's essentially a speculative threading mechanism where the speculative thread is the main program itself. And you just use these otherwise idle cycles to do pre-execution. Okay, that sounds cool. So what are the benefits of this? Yes?
When you hit the load 2 miss in run-ahead execution, you just kind of keep on executing to possibly hit a third?
Exactly, yes. Basically, whenever you had a long latency cache miss, you mark the destination register invalid, meaning you don't trust this value, you'll never get it. That's the assumption. And every instruction that sources that invalid value is also marked invalid. So you drop them very quickly. And hopefully you'll get to a third one. But this picture doesn't show the third one, of course, yes. If there's a third one, hopefully you'll get to it. Of course, there are design choices here. The third one needs to be close enough such that before this miss completes, you'll start the third one also, right? That's one of the downsides of this type of run-ahead execution. That's using the same thread context. If you were doing this run-ahead execution on another thread context, you could always be in the run-ahead execution mode. Yes?
What if load 2 within like the same cache, fit in the same cache line as load 1?
Then basically there's hardware in the processor that merges those loads. And you know that this miss 1 is the same as is going to service load 2 also. You basically mark load 2 also invalid, but you don't start another access. Makes sense, right? That's basically the logic that merges the same cache blocks. It's called miss status handling registers in processors. Yes?
So for the first miss, saving the context to being able to return to the checkpoint, how is that done? Where is it saved? Is it saved in the cache? And then does that also cause some additional latency because then you have to restore the context?
Yeah, certainly there's additional latency, but this is the register file. So the hope is that you're just copying the register file, and you copy the way the modern processors are designed. You don't even actually have to save it anywhere. You just change the pointers that you're using. Does that make sense? Normally what happens is you have registers and you have physical registers, architectural register, physical register mapping. You just don't write to the physical registers that are part of the main thread. You start writing to some other registers that you're not going to expose to the main thread. That's the fastest way of doing the checkpointing, actually. Otherwise, you could also add hardware to flash copy data, but that's a bit expensive. Yeah, all of those details are discussed in the paper. But very good questions. Okay, so you can keep asking, but what are the benefits of this? Essentially, instead of stalling during a long latency cache miss, the processor pre-executes the program far ahead into the instruction stream without stalling for long latency instructions. And these pre-executed loads and stores, independent of the L2 miss instructions, generate very accurate data prefetches. According to our results, you get more than 90%, 95% accuracy actually, which is very high for a prefetcher. And you get good coverage also, as long as your cache miss latencies are large. And this is true for both regular and irregular access patterns, meaning you could be executing something irregularly, and hopefully you'll capture those access patterns because you're really executing the program as if it would execute. Also, you prefetch instructions on the predicted program path into the instruction cache and outer cache levels. We'll talk about instruction prefetching at the end of this lecture. Instruction prefetching is also important, actually. We talked a lot about data prefetching, but instruction prefetching can also benefit performance. There's another benefit that while you're actually executing the speculative mode, you're training the hardware prefetcher and branch predictor. You're kind of going ahead, and you're helping the prefetcher and branch predictor tables. Of course, there's more analysis that needs to be done. It's done in the papers. That shows that this is a good thing because you have future access information. Okay, let's talk about, there's a lot more detail over here, which I will not go into right now, but you'll read the paper so you can take a look. Let's talk about, you need to enter Runahead mode. There's some checkpointing mechanisms that you need to do. We discussed briefly how to do that. You need to process instructions in Runahead mode, and you need to exit Runahead mode. And this is, again, restoring architectural state from the checkpoint. That could, again, be done with pointer manipulation, which is not that hard. Instruction processing is one of the interesting parts. So how do you process instructions? So the key here is, and what makes this appealing is, you don't change the processor that much. Meaning the instruction processing that you do is exactly the same as what you would do in normal instruction processing, except it's purely speculative. Meaning software visible or architectural register or memory state is not updated in Runahead mode. Register state, we took a checkpoint. Memory state, if we get a store, we don't store the data value into the cache, essentially. You could ignore that store. Or you could do it speculatively and change, mark something such that, or add another hardware structure such that that store values communicate to the load, and that hardware structure is completely speculative. That requires some additional hardware, and we added that additional hardware in this particular work. And the other difference is, if you have a long latency instruction or L2 misdependent instruction, you identify them and you treat them specially, meaning their results are not trusted. You mark the destination register as invalid, and you remove them quickly from the instruction window. This is actually general, more general than L2 misdependent. Whatever you want to mark as invalid, you can mark as invalid. But of course, L2 misdependent instructions, you'd better mark as invalid, otherwise they would stall the processor. And the whole point of entering Runahead mode will not be good, right? There's no point in entering Runahead mode if you're going to stall on the next miss. Well, I guess there's one point. You may be starting the next miss, right? Okay, so this is the difference from regular instruction processing. So to be able to do that, there are two types of results that are produced, invalid and valid. Invalid means depend on an L1, L2 miss. And invalid results are marked using invalid bits in the register file and the store buffer. And invalid values are not used for prefetching or branch resolution because these values are not trusted. They're not available yet. An alternative, well, let me finish this and then we can discuss a bit more. So when you remove an instruction from the window, here we don't want to change the architecture that much. Normally what happens in a microarchitecture, in an out-of-order engine is when an instruction becomes the oldest instruction in the processor, it is examined for retirement. If it's completely done, you update the architectural state, remove the instruction, deallocate the resources. So instruction retirement is done in a sequential order, essentially. We do the same thing over here. Whenever we see the oldest instruction, we examine it for pseudo-retirement. If it's invalid, we cannot execute it. So we basically say, remove from the window immediately, deallocate its resources so that it could be allocated for some other instruction. If it's valid, it's removed when it completes execution or when it becomes invalid, because that instruction may become invalid for some reason, right? Meaning that may become a cache miss. Does that make sense? So we don't change the retirement logic that much, but we call it pseudo-retirement because you're not really updating the architectural state. You're really updating this microarchitectural state that's speculative. And you free the allocated resource of the pseudo-retired instructions, which allows the processing of later instructions. And pseudo-retired stores communicate their data to dependent loads through a buffer structure called Runahead buffer. We called it Runahead cache. I will briefly talk about it because this is important for x86 architecture, which has very few registers. Because if you have only 8 registers or 16 registers, you communicate a lot from memory, store and loads. You have a lot of stack communication because of stores and loads. So we propose a structure, which is when a pseudo-retired store speculatively writes its data in invalid status to a dedicated memory called Runahead cache. And the purpose of the Runahead cache is to communicate data through memory in Runahead mode. A dependent load reads its data from the Runahead cache. This way, hopefully, if you have some address generation computation that happens due to the store load dependence, you'll get the address right. Okay. Now, the reason we add this Runahead cache is it's a purely speculative structure. It's the goal is to ensure that we don't update the data value in the real cache, which is really you don't want to update the data value with any store, right? That's the idea. You don't want to run into this coherence problem that you discussed earlier. Okay, this doesn't need to be always correct, so the size of this can be very small, as we show in the paper. And this is only really important when you have a small set of registers. If you have a large set of registers, 32, 64, then this may not be that important, as we show in other papers. Okay, what about branches? Because branches are interesting in this run-ahead mode. You're speculatively executing, and you get a branch whose value is dependent on something invalid, meaning it's dependent on some L2 miss, for example, or an instruction that you marked invalid because you don't want to execute it because it takes too long. Now, this is not a problem. If the branch is valid, it's not a problem because you resolve and initiate recovery on the speculative path if you mispredicted the valid branch. But if it's invalid branch, you cannot resolve it because you don't know the data value. You don't trust the data value. And if you mispredicted it, meaning, but you don't know if you mispredicted it because you cannot resolve it in this mode. If you mispredicted it, then you're on the wrong path. And you don't know you're on the wrong path, and you will stay on the wrong path until the end of this run-ahead execution. And this may or may not be good. And in our analysis shows that this is not bad, but it's better to be on the correct path. So if you can actually somehow figure out which invalid branches are mispredicted, you can speculate, you can initiate a recovery speculatively in the speculative mode. It sounds interesting, right? Levels of speculation. Okay. Okay, so this is the picture that we had, ugly picture, in my first paper. See, I learned so that my students don't draw these ugly pictures. That's how things improve in the world, you know. If everybody goes through the same thing, then the world will always be ugly. Okay, I'm not proud of this picture, but anyway, this resembles a Pentium 4 processor, which we evaluated this on, and you can see that the additional entries are relatively small. So there's this architectural register file, which is really pointers, as we discussed, but you could also do some other things that we discuss in the paper that's separate. There's the invalid bits in the register file that you need to keep track of. There's invalid bits in the store buffer, and there's run-ahead cache. So this part is the most complicated part, load store logic. I'm not going to go through this in detail. I described some of it, but you can see that this doesn't change the processor that much, although it does touch a lot of parts of the processor. So even though it doesn't add a lot of hardware, it touches the flow of execution in the processor quite a bit. Okay, let's talk, before we look at results, let's talk about some advantages and disadvantages. Like every idea, this has advantages and disadvantages also. Now, hopefully it's clear that this is a speculative pre-execution or threading mechanism for prefetching, right? You create the speculative thread dynamically. So the advantage is, because this run-ahead execution follows the program path, you generate very accurate prefetches for data and instructions to all cache levels. It's simple to implement. Most of the hardware is already built in. There's no waste of hardware context in this particular implementation. You use the main thread context for prefetching. So it's very frugal in that sense. There's no need to construct a special purpose pre-execution thread for prefetching. You're kind of constructing it inside this run-ahead mode. But there are disadvantages also, because now you're executing extra instructions, right? That's true for all pre-execution based mechanisms, actually. But in run-ahead execution, it could be maybe more true potentially, because you're really not constructing this thread very, very, let's say, frugally, because you're using the main thread, right? And you may be executing a lot of instructions and you may not have enough time to get to the next load, but get to the next cache miss, right? Because you're getting out of this run-ahead mode by the time the first cache miss that initiate entry into the run-ahead mode comes back. And this is a problem, and this is a problem that we later solved with some prediction mechanism. You can basically, one of the things that we introduced in a later paper is to predict whether an run-ahead execution period is going to be useful or useless or short, or overlapping with some other execution period, and eliminate as much as possible those inefficient run-ahead execution periods. And if you do that, you can actually reduce the extra instructions significantly without losing performance benefit of run-ahead execution. So there are solutions to this. And NVIDIA Denver, for example, implemented a form of run-ahead execution, which is very similar to what we've discussed. They actually implemented some of these efficiency mechanisms, because otherwise the extra execute instructions may be a lot. Yes?
Yeah, I mean, maybe touching upon that also a bit. You always, so when you execute something speculative, you always mark the results as either valid or invalid. Can you use valid results in your main thread so that you don't have to recompute them?
That's a great question, basically. We have looked at it. we didn't see a lot of benefit in out-of-order execution processors because it turns out those valid instructions are usually not on your critical path of execution. But Sun folks, later Oracle folks, they implemented this ROC processor. They actually have a paper where they actually have a mechanism for reusing this in an in-order processor. And they show significant benefit for reusing those results. So valid results they keep and they integrate into the pipeline. They have a nice execution model. I'm going to mention that paper later on. So that's a good idea, I think. Not easy to do. It complicates the hardware, but it may lead to a different execution model like they did. I wish Oracle didn't buy them and they could continue doing good work. Sorry, Oracle folks. Because these were actually hardware designers that implement a lot of good processors and tested a lot of ideas. And Oracle at some point killed the hardware part of their company because the hardware part came from Sun and they never got it well integrated, I think. Okay, yes.
Will this benefit from some of the software related things like unrolling the loop more so that you can actually do more address calculation instructions before?
Yeah, potentially, yes.
Aware of this, would it benefit more?
Yeah. I think potentially, yes, definitely. Like you could actually write programs that can benefit from Runahead execution more by trying to cluster the misses. Whenever you get a cache miss, ideally, all of the other misses should happen around that cache miss, right? So that's called memory level parallelism. You could try to maximize the memory level parallelism in your program or miss level parallelism in your program as much as possible. So it could be compiler optimizations. It could like a loop unrolling. It could be even software writing. Okay.
Also, like in general, probably vectorization would also benefit this, right? Because if you can do, so basically the latency of the valid part is overlap with the latency of the fetch for the invalid part. So the latency of the valid part is more, which could be the case if you have more computations, such as vectorization, then you would overlap that latency. Yeah,
I mean, certainly, you could do that. I mean, vectorization is useful if it parallelizes a lot of misses, potentially, right? Yeah, I agree. Okay, so there are other disadvantages. You're limited by the branch prediction accuracy because when you get a branch prediction, mispredicted invalid branch in Runahead mode, you cannot recover, right? But this is true actually for any large instruction window mechanism. So if you improve the branch predictor, this becomes better. And people want to improve the branch predictor. That's good. A big limitation is you cannot prefetch dependent cache misses. If the address of the first miss, or if the data value fetched by the first miss is used as an address for the next miss, or address generation, using the address calculation for the next miss, you cannot do that. Right? So one way of getting rid of this dependency is predicting the address. And we have proposed some mechanisms. And I'm going to mention that briefly, but we're not going to go into the detail. This is a fundamental limitation of this sort of prefetching. Dependent cache misses are very hard to predict. But if you couple this with content-directed prefetcher, actually, it is not that bad. The effectiveness is limited by available memory level parallelism. We discussed this basically. If you enter Runahead mode and you cannot find any other cache miss, even though you don't have this dependent cache miss problem, everything's independent, but you cannot get to the cache miss because it's too far away in the execution stream, then you're not going to get much benefit. Ideally, you would like to cluster your misses as much as possible to each other, and software optimizations can help. Another limitation is prefetch distance, meaning how far ahead your prefetching is limited by memory latency, or more accurately, how long you stay in Runahead mode. If you enter Runahead mode, and if you stay in Runahead mode only 50 cycles, you may not get a lot of benefit. If you enter Runahead mode, and if you stay in Runahead mode 500 cycles, you may get a lot more benefit, right? Because that's your distance now. Right? And later work is going to target that, and we target this in our efficient Runahead execution work. We try to identify these short Runahead periods that happen based on some loads, and we filter them out, meaning and did not enter Runahead mode if you actually think or if you predict that it's going to be very short. And that gets rid of both extra executed instructions and useless periods. So you can optimize this a lot. And that's what NVIDIA them were also implemented because they don't want to waste, clearly. Okay, so this is a result from our original paper. We actually worked with Intel and used a lot of interesting workloads from Intel suites that they used to design their processors at the time. And you can see that there are 4 bars, average is over here. The baseline is no prefetcher, no Runahead. Actually, that's one baseline. The real baseline is you have only prefetcher. which is a streaming prefetcher like we discussed, or locality-based prefetcher like we discussed earlier. And the next bar is only Runahead. So you can see that only Runahead is actually a bit better than only prefetcher. But the best is when you combine both of them, prefetcher plus Runahead. And that gets you about 22% on average performance improvement compared to only prefetcher. So it actually improves performance across the board. There are very few workloads that do not benefit or degrade. Degradation is hard to see, but it's possible to degrade performance, of course. Okay, I'll not go into this detail. You can read the paper for more. And we compare this to large windows. And the reason why we did this, actually, people were trying to, I mean, memory latency is always a problem, right? One way of tolerating memory latency is execute more instructions concurrently, and you have a very large window. So your window never stalls, right? Meaning you have a cache miss at the head of the window. It takes 500 cycles, but you made your window huge, maybe 5,000 entries, and you never stall. But you're very speculative in your window, of course. So people were trying to build these huge processors with very large windows at the time. So our argument was basically, we should explore more efficient ways of building systems, meaning keep the small window, but add Runahead to it. And that will get you some of the benefits of this large window. That's the idea. And we compare that, for example, this is our 128 entry window baseline, which was very similar to Pentium 4 at the time. And if you do 128 entry window plus Runahead, you get a lot of benefits. And this is better than 256 entry window, which is doubling the window size. Very close to a 384 entry window. So it kind of gets you the benefit of a much larger processor. Okay. So the philosophy was be more frugal, be more efficient. Don't build huge things because huge things are expensive. Okay, we're going to get back to that. So we were also very interested in how does this impact in-order versus out-of-order processors. This is the in-order baseline on the same workloads. In-order plus Runahead buys you some performance. This is the out-of-order baseline, the red bar over here, and out-of-order plus Runahead. You can see that Runahead is good on both in-order versus also out-of-order, but it gets you better percentage improvements in in-order processors, almost 40%. And the reason is if you have an out-of-order processor, it doesn't have a lot of latency tolerance. If you have an in-order processor, it doesn't have a lot of latency tolerance. Okay, we're going to get back to that also. But this is actually very interesting studies to do. If you're doing computer architecture, it's always good to study what is the benefit of out-of-order versus in-order. You can see that this is why people implement out-of-order processors. This red bar is much larger than the blue bar in terms of performance. Of course, you can also evaluate energy, but you can do that. So the Sun folks who implemented the ROC processor before they were bought by Oracle were the ones that took this idea first time. They were building actually commercial processors for transaction processing, online transaction processing, etc. It's very similar to Runahead. They implemented it on an in-order processor. They called it Scout because industry needs to change the name, you know. Scout is not bad, actually. I like the name. It's better than hyperthreading that Intel uses. I don't know what hyperthreading means. At least here you're scouting, right? You're a scout and you look first before the main thread reaches that place. Okay, so this is their results. I like their results in multiple aspects because it shows that this sort of idea is also efficient in terms of cache space. For example, no Scout is no Runahead. If you implement it on a processor with 512 kilobyte cache, you get 40% better performance, which is interestingly very, very similar to what we have shown with in-order processors with 512 kilobyte cache in our paper. So interesting. These are different workloads, but similar benefits. And if you implement this Runahead execution on a processor with 1 megabyte cache, it gets you the performance of a non-Runahead processor with 8 megabyte cache. So instead of investing 7 megabytes extra hardware, just implement Runahead execution. And that becomes larger when the curve shifts to the right. As you can see, it buys you 12 megabytes if your baseline cache is already large, because this is kind of the diminishing returns from larger caches. Okay, so basically effective prefetching can improve performance and reduce hardware cost. This is actually true for different prefetching mechanisms also, not just Runahead execution. If you have a very effective prefetcher, you don't need large caches. Okay? For example, what you're doing is only streaming. If you remember the stream buffers paper from Norm Juppy, you have a data cache, and the next level is really stream buffers. There's no second level cache. And people have looked at the effectiveness of second-level cache versus stream prefetchers. And if your applications are only doing streaming, you don't need the second-level cache. Unfortunately, streaming is a very specialized access pattern. Runahead is more general. Runahead can target actually many different access patterns. So it may be easier to sell Runahead as a way of replacing a large amount of cache without removing the entire cache. That's what they're trying to do over here. And they argue that basically, if you actually remove this amount of cache, you can use the same area for more cores. And their applications are actually highly parallel. So they both improve performance of a single thread as well as improve performance of a multiple thread by using prefetching nicely. Okay, so this is the original paper that we wrote. This is the Sunrock paper. And this is the paper where they decided to take it to the next step, meaning not just Runahead execution, but reusing some of the results, some of the valid results that are generated. I will not go into this detail. It's a relatively complicated architecture. But if you're interested, I would recommend reading it. It's a bit hard to read, frankly. But what they're trying to do is there is one processor they call the speculative thread processor. There's another thread, I should say. There's the speculative thread and there's a non-speculative thread. And speculative thread always runs ahead of the non-speculative thread and feeds instructions to the non-speculative thread. And essentially, it's a form of slipstream architecture, if you have seen slipstream. We may talk about that later on. But it's doing it when cache misses happen. Make sense? Hopefully this gives you an idea. I cannot describe the whole architecture because it takes a long time. Okay, so this was also implemented in IBM Power 6. The way they implemented it is actually, they didn't use the same hardware context. They actually launched Runahead execution on a separate hardware context to prefetch for the main thread. So they actually didn't have the flush penalty at the end of Runahead execution. So that was good from their perspective. And they actually wrote papers about it. Okay, you can read more. NVIDIA also implemented Runahead execution. They actually had a lot of ideas in this paper. Let me see what I want to cover over here. They have this paper. Some of the things that they have over here are actually very similar to what we have found. For example, let me look at that. Runahead complements the hardware prefetcher because it's better at prefetching non-strided streams. And it trains the hardware prefetcher faster than normal execution to yield a combined benefit of 13% on spec-int and up to 60% on spec-fp. What else? I mean, you can read it for more detail, but I guess what they wanted to do is have a, they didn't want to implement out-of-order execution in this case. They wanted to implement Runahead execution. And they have a very heavily superscalar processor, as you see over here. And I guess they have some benchmarking results as much as they can report. So these Runahead type of features help Denver outscore a Cortex A15, which was their baseline, this ARM Cortex A15, by more than 2.6x on a memory read test when you use the same SoC framework. So it's just the SoC is the same, but the microprocessor is different, and they get a 2.6x higher performance, which is pretty good, actually. And that's why they decided to implement it. So it's very interesting to see papers building on your paper relatively quickly, although a Denver paper is a little bit later. Okay, their enhancements. I've already given you some ideas over here. And we've written papers on Runahead enhancements. Most of these are in my thesis, these three. This is not in my thesis. Maybe we'll talk about it at some point. And later, like 10 years later, we actually improved Runahead. I'm going to talk about that briefly. But basically, there are downsides to this idea also, right? And one of the biggest downsides that we solved almost immediately is the energy inefficiency. Right? We discussed this. A large number of instructions are speculatively executed. And by identifying which Runahead periods are not efficient or useful, you can actually get rid of those Runahead periods. And we basically looked at dynamic mechanisms to identify that. For example, if you have a load instruction that calls into Runahead mode and that Runahead mode doesn't generate cache misses, you can keep statistics whenever that load instruction calls entry into Runahead mode. And if you're based on past information, if you don't get cache misses during Runahead mode, don't enter Runahead mode again. Or you time how many cycles you stay in Runahead mode based on entry into Runahead mode under some conditions, like a program counter. If you consistently get very short Runahead periods, the next time you see those conditions, don't enter Runahead mode. So these are ideas basically that are implemented in the efficient Runahead execution paper. And I think these are actually very simple ideas that make the Runahead idea work. I wouldn't implement Runahead idea without these efficiency mechanisms. Otherwise, it's just too expensive. Expensive in terms of number of instructions. You have a question? Yes?
Like, why instead of like, why not just like skip over that number of instructions and try to look for the checklist instead of like disregarding Runahead?
Yeah. I mean, you need to execute something, right? If you start skipping over, then you may not have values available. Right.
We already know from previous like statistics that under that condition, if we run that amount of Runahead, then we will not find any checklist that we should skip ahead.
Yeah, so our goal here was to eliminate the periods that are useless, right? We don't know where we will find the misses. You can do more by trying to figure out where the misses will happen and jumping to that area where you can find the misses, but that requires a lot more analysis in the paper, in the program. We have looked at those ideas like that, and I would recommend looking back again. We've never found anything that could be done easily. Right? But eliminating a useless period is more easily done because you kind of know, oh, this was useless before, so it's probably going to be useless again. And there's repeatability in that behavior. Okay. The other issue is ineffectiveness for pointer-intensive applications because you cannot parallelize dependent cache misses. And we actually have a solution or partial solution to this, and I suggest that you read it. The other issue is irresolvable branch mispredictions in Runahead mode. You cannot recover from mispredicted L2 misdependent branch, and that's why we actually developed wrong path events and wrong path memory reference analyses. And the idea in wrong path events is, what we tried to answer is, okay, you don't know whether you mispredicted a branch because you don't have the data values available. Can you use some other information in the processor to guess that you have mispredicted the branch? For example, if you somehow got a null pointer dereference in Runahead mode, probably you mispredicted something. Right? So that could be an indicator of you're on the fact that you're on the wrong path. If you're getting a lot of cache misses for some reason, that could be another indicator. If you're getting a lot of TLB misses, that could be another indicator. Right? It's good to think about this basically. The wrong path events are events that you monitor in the processor that may be an indicator of the fact that you may have mispredicted the branch. And I think there's still a lot of potential in this idea. There may be other events to be discovered. Maybe it needs to be done with machine learning. Okay, and then there's the limited Runahead distance issue. Runahead ends when the first miss that caused it returns. Can we actually continue execution? In my thesis, I explored this a little bit, but the way we actually finally made it better is after 10 years, let's say. That's the continuous Runahead. So I'm going to get to that. So these are some papers. You can take a look at them. I'm very proud of these papers, but it's fun to write them. Let's talk about continuous Runahead. So this is in Milad's thesis. He was working on Runahead and he reached out to me and we developed this idea, continuous Runahead. And the issue is basically Runahead execution coverage is relatively small. Even though it improves performance a lot, it reaches a small fraction of Runahead reachable misses if you kept executing. The problem is you don't keep executing. You go back to the original instruction that caused entry into Runahead mode and flush the pipeline. So can we actually keep executing in a nice way? Essentially, Runahead execution interval is very short. And these are the things that we eliminated with efficient Runahead execution. But here we ask the other question, instead of eliminating these, can we keep going and make it 600 cycles or whatever? And yeah, there's some analysis over here, which I'm not going to go into. Yeah, the basic idea is keep Runahead going even after long latency cache miss is serviced. And to be able to do that, clearly you need another context. And how do we actually do this? We identify, there are multiple ways of doing this, but in this particular paper, we identify chains of instructions that lead to long latency cache misses. We keep executing each chain of instruction in a loop in Runahead mode using some specialized Runahead execution hardware we call continuous Runahead execution engine. This could be a separate core, but one interesting thing that we did is the goal of this continuous Runahead execution engine is to continue generating long latency cache misses. And it's located in the memory controller. So we basically wanted this to be in the memory controller. It's essentially a small core in the memory controller that keeps generating cache misses. We didn't want it to be yet another core. The idea is if you're in the memory controller, you can be actually much closer to memory and generate the cache misses and bring them into the hierarchy. And you stop executing the chain after a fixed number of instructions. And the key results, we actually increase the coverage of Runahead from 13% to 70%. And you get a lot more performance gain over best Runahead implementation in single core systems. And if you're interested, you can look at more detail in the paper. But this is one of the state-of-the-art Runahead mechanisms. Of course, it has more complexity, right? Now, this is not the frugal Runahead anymore. You have another core that's doing Runahead for you. We try to minimize the complexity as much as possible, but there's still complexity here. And there's a lot of analysis in the paper that compares, for example, Runahead. This was the best Runahead implementation at that time. There was a lot of research after my thesis. CRE is the continuous Runahead engine. And then streaming prefetcher, the global history buffer prefetcher, streaming prefetcher plus continuous Runahead, and GAP plus continuous Runahead. You can see that continuous Runahead together with the prefetcher is the best implementation in terms of performance in general. Okay, so that's the paper in 2016. And if you're interested in improving on Runahead, I suggest building on this one. And this is, I think, the nice thing over here is this is like processing near memory, right? You're really doing speculative threading in the memory controller. And maybe you should do it in the memory side going into the future. It's good to think about these. Okay, there are other works that have actually improved on Runahead. Ajay and Aitani from Ghent University, working with Liev and Eekhout, they did a lot of good work on Runahead execution. This is one of their papers. And the idea is actually, I think one of you mentioned vectorization, and they had a similar idea basically. They had, instead of having scalar operations, they vectorized the scalar operations so that they could generate many misses for independent loads at once to essentially increase the memory level parallelism. And they do this purely in hardware. And proactively prefetch, they also proactively prefetch even when a core is not stalled. So there's more in this. I'm not covering everything over here, but this is a nice paper that improves upon the basic Runahead mechanism by vectorizing scalar load operations to get more memory level parallelism as quickly as possible. Right? And this paper actually received the best paper award at Micro as recently as 2023. So that means that people actually value these fundamental improvements, as you can see. It's good to see that work that builds on your thesis, even after like 15 plus years later, receives best paper awards. Yes?
This will probably be even more relevant for things which are operating on even bigger pieces of data, things like tensor instructions or any other systolic allocations.
I believe so, yes. I mean, I don't remember if they looked at those things, but if your data sets are larger, certainly packing as much as possible so that you don't do things sequentially, you do things in parallel, and it can tolerate more load misses that may be happening in larger structures is good. Yeah, so it may be good to examine that. You may want to read the paper and see maybe there's some more opportunity. And I believe there's more opportunity actually here. They may have some more paper after some other paper after this. So I'd recommend looking at the later papers as well. Okay. So there's more work, but I cannot cover everything. But let's go back to the execution-based prefetchers. Essentially, Runahead is an execution-based prefetcher, right? You pre-execute a piece of the pruned program solely for prefetching data. And that's what we're doing over here. You pre-execute the main program solely for prefetching data. And you actually reduce the program. For example, in the efficient Runahead paper, we said that you can drop all of the floating point instructions because very likely those floating point instructions are not going to affect your address computation unless you're doing something weird in your code. They may affect your mispredicted invalid branches because you may branch on a floating point data, right, comparison. But very likely that's not the case. So if you ignore floating point instructions, you get rid of a lot of useless instructions, and you can make faster progress in the program stream. So you can actually prune the program, as you can see. And clearly, there are advantages and disadvantages of Runahead and other execution-based prefetchers. I'll let you think about those. I think one of the advantages of Runahead is very, very frugal, but the disadvantage is it's very frugal, right? Meaning it may not cover a lot of the misses. So this could be an advantage and disadvantage. In terms of hardware implementation costs, it's maybe cheaper than other prefetchers, certainly. Can you make Runahead even better by pruning the program portion executed in Runahead mode? The answer is yes. I've given you one example. And continuous Runahead is another example, actually, of this. It's basically constructing a chain of instructions that is executed in a looping manner. Okay. So this brings me to taking advantage of pure speculation. Basically, Runahead mode is purely speculative. The goal is to really find the cache misses that one would otherwise stall execution on. How do we achieve this goal most efficiently and with the highest benefit? I don't expect to answer this right now, but this is actually an important question to think about. And people have looked at this question. Essentially, you would like to ideally find and execute only those instructions that will lead to cache misses that cannot already be captured by the instruction window, of course. And there's a lot of work that tries to do this, both in software as well as hardware. And if you're interested, I'd be happy to talk, but this is an interesting area. So now let's cover the pros and cons of execution-based prefetchers. We did a deep dive into Runahead as an execution-based prefetcher. The big pro of these execution-based prefetchers is they can prefetch pretty much any access pattern, essentially. Even linked list patterns, assuming you actually raise the code earlier. Runahead may not be able to do that, but some other execution-based prefetchers are more powerful than Runahead because you could actually do a linked list traversal much earlier in the code, right? So any access pattern is fair game and coverable. It can be very low cost, like Runahead execution, right? Especially if it uses the same hardware context, because the processor is equipped to execute the program anyway. Right? Speculative thread is just another program. And if you're executing the main program, you're already executing the same thing. It can be very bandwidth efficient, actually. Runahead execution is very bandwidth efficient, even though it may execute a lot of instructions if you don't employ some of the efficiency techniques. It doesn't cause extra bandwidth because a lot of the prefetches are very accurate. The downsides, always, again, with execution-based prefetchers is they depend on branch prediction accuracy. They also depend possibly on value prediction accuracy, because you may predict the values that go into the speculative thread, right? So that you can cut the dependencies from the main thread and the speculative thread. And mispredicted branches that are dependent on missing data throw the thread off the execution path. That's true for all of these speculative threading mechanisms. So it's good to have better branch prediction in general. It can be wasteful. They speculatively execute many instructions. We've seen that with Runahead, but that's true for actually any execution-based prefetcher, because you're executing some instructions. And if they're not going to provide benefits, you're actually increasing the number of instructions you're executing without commensurate benefits. So throttling mechanisms to actually reduce this waste, identifying inefficient incarnations of speculative threads is very important. We saw examples of this in Runahead, but that's true for all execution-based prefetchers. It can also occupy a separate thread context, right? That's also waste, because if someone else needs that thread context, you're using that thread context. You're reducing your throughput, system throughput, essentially. And then there's complexity in deciding when and what to pre-execute. That's really actually important. Okay. So maybe I'll cover this and then we'll take a break. So this Runahead execution, I think, is close to my heart, as I said. And if you're going to do a PhD, I'd recommend doing things that you're really excited about. That's the whole purpose of a PhD. Otherwise, there's no point in doing a PhD, in my opinion. You should really be excited about doing something for a long time. And we've been lucky that a lot of people actually adopted ideas from Runahead. And we received the Test of Time Award 18 years after the paper was published. And I gave a talk describing what was our thinking at the time. And this is actually what we were thinking. This was early 2000s when we developed this idea. And there was, as I told you earlier, there was a large focus in the industry on increasing the size of the instruction window. And there was a huge power problem. Pentium 4 actually was one of the most power-hungry machines that was ever built at the time. Today we have these GPUs that are crazy, but Pentium 4 was crazy at the time. And if you wanted to increase the size of the window, you'd actually make all of the processor structures much larger. And basically, there was a big push for designing bigger and more complicated machines. And this was actually true at Intel also. Intel actually wrote several papers on large instruction window machines, which is a good area of investigation. But we thought other areas should be investigated as well. So we wanted to have a different way of thinking. Essentially, Runahead was a different way of thinking. The idea was to keep the out-of-order core as simple as possible and as small as possible, at the expense of some benefits, meaning you don't get parallelism across different instructions that are not going to memory. But we wanted to tackle the memory problem by keeping the core small. And we wanted to use aggressive automatic speculative execution solely for prefetching purposes, instead of increasing the instruction window size to cover benefits of memory level parallelism, let's say. And this is actually synergistic with prefetching and branch prediction methods. So a lot of interesting and innovative ideas ensued. I've given you some examples of that. But when we gave the talk, we also identified, actually, when we were doing the research, after we did a lot of the research, we used to call the scratch mode execution, Runahead execution. Scratch mode means you have a mode where you scratch all the results, SME. So if you look at the original code that I wrote, it's all SME. When we wrote the paper, we called it Runahead execution because we discovered that there's this paper in ICS in 1997, which was relatively forgotten at the time. It was a beautiful paper from Dundas and Mudge, which essentially does a form of Runahead execution in a very small in-order processor. But we adopted the terminology that they adopted. So we changed everything in the paper to, not in the code. Code states as SME because nobody wants to go back and change the code, right? Code stated as SME, but we changed the paper such that we used the term that they used, Runahead execution. We used some of the terminology that they used. So we did this for out-of-order execution, and we added some of the other concepts. For example, they stopped execution on an invalid branch. We showed that that's a bad idea if you have a large instruction processor. You don't want to stop execution on an invalid branch because that gets rid of a lot of the benefits of Runahead execution. So some of the design choices we made were very different than them. But we did acknowledge them. So I think this is the right thing to do. It's very important to acknowledge prior work. And I'm glad that we found this work. And I talked to Jim Dundas a lot, actually. He used to work at AMD, and he was very happy that we acknowledged his work, and it made his work more visible afterwards. I don't know where he's right now, but if he's listening, hello. Okay. There was also another work that was quite inspirational. This was in ASPLOS Wild and Crazy Ideas session in 1998. This is actually, this is the paper, a single page. You can read it almost if you have good eyes from the back. Not me. But this paper is actually out of the box thinking. Basically, a lot of people are building large instruction windows, trying to exploit instruction level parallelism of instructions that take 3-5 cycles or whatever. And this paper said from Andy Glue, essentially forget about ILP. What we really care about is MLP, memory level parallelism, because memory is the big bottleneck. So we should really design processors that cater to discovering more memory level parallelism. And there are many ideas over here. You can see 7 ideas. But essentially, Runahead is an example of this idea, not exactly as described over here, but further reduce the cost of very large instruction windows by throwing away anything that can be recomputed based on data and registers or cache. I guess that's a different thing. Don't store speculation because the oldest instruction in the machine is a cache miss. Let the front end of the machine continue executing branches, forgetting data dependent on cache misses. You can see that the idea is somewhat similar, although they have a different implementation in mind, which is front end continues, back end still executes instruction. You have a large instruction window, which we're going to discuss actually later when we get to instruction prefetching. So it's good to actually write papers like this. And I have a lot of respect for Andy Glue for doing work. I actually overlapped with him in many companies, and including AMD at Intel. And he's a good idea generator. Okay, looking to the future, I think microarchitecture fundamental topics are actually important, especially memory-related microarchitecture, I should say. It's also fun. It's also impactful. And Runahead is also a great example of harmonious industry-academia collaboration. We worked really well with Intel folks because they had the same mindset. At least Intel folks who had the same mindset. We worked really well with them. And I think fundamental problems will always remain fundamental, like branch prediction, prefetching, and they will be fun to solve. That's right, it's fundamental. Yeah, and they will require fundamental and creative solutions. So it's good to work on these problems, even though they may be hard. I think prefetching is a lot easier than branch prediction these days, but it's important to work on them. So this was the citation for the Test of Time Award when they gave us the Test of Time Award. I think they liked, it's a pioneering paper that opened up new avenues in dynamic prefetching. And it spawned off a new area of ILP enhancing microarchitecture research. And clearly we've discussed some of these other things. So when we were doing this research, actually, there was a lot of pushback also that we received. A lot of it from people who were building large instruction windows. They didn't believe some of our results. We had to prove them wrong or prove our results right. and prove them wrong and not believing our results. So it wasn't easy basically to actually convince people. And that's always the case, because some people are always invested in doing something, building a large instruction window, and they don't want to be bothered by doing something different, right? For good reason or bad reason or malicious reasons. There are all kinds of reasons, clearly. So we had to prove our results, and a lot of people actually liked the results. There's also another paper, Itanium, for example. Unfortunately, I don't talk about Itanium that much because it's kind of like Titanic. It's kind of dead Titanic, It actually did some RNA execution similarly to how Andy Glue envisioned it. It was inspired by our papers, but what they implemented in the end was the front end of the machine was actually uncovering cache misses, and the back end of the machine, while the back end of the machine was stalling. So that's kind of another implementation of Runahead. So we essentially followed our passion. We did not get derailed by people, but we were very scientific in what we demonstrated in the end. So it's good to be resilient, as you can see, and you believe in an idea. And if the idea works out, that's good. If the idea doesn't work out, you don't be dogmatic about it. You just move on. Right? That's science in the end. You follow your passion, but you follow it to the point where you actually tested the idea. And if the idea works out, that's great. In this case, it worked out, so we were happy. That's why I think it's important to focus on learning and scholarship, as opposed to what other people may be telling you, because other people may be telling you, don't work on idea X, right? It's always good to explore different ideas than what the mainstream is exploring. And the quality of your work in the end depends on your impact. You've seen these slides before. So there's more on Runahead execution. We actually have longer lectures from the past. You can take a look at it. And you can take a look at my PhD thesis. And I rewrote my first paper completely in my PhD thesis, because when I was writing my thesis in 2006, I went back to the paper that I wrote in 2003, and I said, this is terrible. Let me rewrite it completely so that it makes sense. It makes better sense, at least. Yeah. So it's good to do that also. Okay. I think this is a good place to stop and take a break. Let's take a break until 3 p.m. And then we're going to cover a little bit more prefetching, and then maybe multiprocessors. Let's see. What? You need to extend Genster probably so that it makes sense. Exactly. Yeah, it's been almost 4 years since Genster. Yeah. It'll be 4 years by the time of defense, which is hopefully in... Yeah. I hope not. Okay, you're not defending. It's going to be 4 more. Okay.
And they said to leave 2 days for the DOI to register. That means on Monday.
Yeah,
So yes, yes. I will make I have made it already.
Yeah.
But I will
The one, so you can submit it. The one I
yes, exactly. I will do it.
Yeah. But I mean, I think this is, you may be able to update it on the F1000 website also. I don't know.
Okay. I will check that.
Very good one still.
Yes, yes. We just make it a little bit more organized and then update. I think it's the flow should be nice. It's looking very nice.
This is your talk, right?
Yeah.
The talk that I saw.
Yeah. So this is our background. I mean, I thought they don't need it, but anyway.
It's good to have, not everybody over there is actually genomic speakers.
Yeah.
It's so easy.
Like the other part of stuff.
Yeah.
Roughly solutions so far. Our goal, just make these. Then merging stuff, meaning grains and numbers. Save. Encryption is now into side.
Yeah, that's good. Yeah, and also a point, have something that they can scan for the workshop.
Yes, yes, I'm putting part of the email. Yeah.
Yeah, definitely.
Yeah, it's a good question. Knowing everything about computers, but not this.
Yeah. Sounds good. should be good.
I hope we get the barcode with the URL DOI for Monday.
Yeah, I mean, you should get it. If not, we'll ask them. We'll tell them we already submitted. I need to register also,
Mhm.
because I forgot to register.
Ah, okay.
Yeah.
Do you also need registration?
What do you mean?
You're older, right?
Yeah, but I still need.
It's actually a nice place at a nice time, really.
Yeah.
Huh?
You can tell Constance that's good.
She's being let's say priest,
Yeah,
not a priest, but
not at the right time.
yeah. Well, you think that they should change the baptism timeline of their child so that.
Exactly. Yeah.
Okay.
You can say this is more important. I gotta go there.
I'm happy you've mentioned it, so the baby should have come later.
Well, it's hard to change at this point. Or no, it's a big coming.
No, it has a
It's already right. If there's a possibility of doing that, they should do that. Right.
I was in the conference.
Or the Zoom button. We'll take it the Zoom baptism.
Okay.
This is like people do telemedicine, right? You can do
Yes.
telebaptism.
I wonder if they've done it so far, but I'm sure someone has thought about it.
Yeah, I'm sure.
Okay, I go community top time, so
Okay.
it's a very good.
Sounds good. Thanks.
But maybe now that's something that we can mention. Then you can actually how this can be. Because now that we are trying this is not that we can say once we have this, since the input is so much energy. When you get special section information, and actually discuss say that one. I don't care what's just get over the There's also so have those so that's why I think it's good to say but maybe we should also show divide this that's why I think we should include mixed also. Right section, I agree.
Yes.
Okay, let's get started. So now we're done with Runahead execution. Are there any questions came to your mind? Okay, let's move to instruction prefetching then. I'll cover this relatively quickly. So far, you talked about data prefetching. In Runahead execution, we also talked about you execute instructions, you prefetch instructions also, because you may miss in the instruction stream. So instruction prefetching actually is similar to data prefetching, but maybe potentially easier. Essentially, the idea is to predict which instructions or instruction cache blocks will be needed by the program and fetch them before they're needed by the program proactively. And all questions we discussed apply to instruction prefetching: what, when, where, and how. And instruction prefetching can be done very similarly also, software, hardware, and also thread-based. The major difference is instructions are accessed sequentially. Recall the von Neumann model. In von Neumann model, sequential execution is a key pillar in addition to stored program computer, unless there's a control flow change, of course, unless there's a branch, essentially. So usually, simple streaming or next line prefetching is very effective. But this doesn't work if you have a control flow change that's not in the next line, right? So people augment things. So next sequential instruction prefetcher, the key idea is to always prefetch next n instructions or cache blocks after a demand instruction. This works well when program executes sequentially without branching. So you've already seen the next line prefetcher, right? We also called it next sequential. And this is actually first used as early as in IBM system 3691. This is a beautiful paper by Anderson et al. In 1967. So essentially, they have an instruction buffer that prefetches instructions. And I'm not going to go through this, but they have a flowchart of how the instruction prefetcher operates, essentially, instruction fetch and prefetch engine. It's a next sequential instruction prefetch engine, basically. People have, let's say, talked about this idea more recently also and extended this next sequential prefetcher. There's a selective next 4-line prefetcher, for example, one example. You prefetch only those instruction blocks in the next 4 blocks that were useful when prefetched last time. This requires some metadata to decide which of the 4 lines to prefetch. So it's similar to what we have discussed earlier, right? You need to have one prefetch bit per cache line. You set on prefetch fill, reset when you used, and you have a metadata table to track usefulness of cache blocks. So this aims to be more accurate than a naive next 4-line prefetcher, because the next 4-line prefetcher may not always, if you have a branch, for example, you may not use all of the 4 lines, right? Of course, you need more metadata. And people kept improving this sort of prefetcher. There's this entangling prefetcher, which is essentially trying to solve the problem of this sort of instruction prefetcher being late. A program demands the instruction before the prefetch finishes. So if you want to be less late or timely, this is what the paper does. For a given iCache miss, it calculates its latency. And it basically correlates this iCache miss address with an earlier iCache access address that's far enough such that you trigger prefetching for an address when a correlated preceding iCache access address is encountered. That's the idea, basically. You correlate the one that you're going to miss, the miss address, with an access address, and pick an access address that's far enough ahead such that you don't wait. It's an example of a correlation-based prefetcher, basically done for instructions. There's some more detail in the paper, but I'm not going to that. One commonly used approach is fetch-directed instruction prefetching. So if you're actually fetching, you're at the front end of the machine, right? The back end of the machine is doing something else. You can actually decouple the front end and the back end of the machine such that the front end of the machine kind of runs ahead of the back end, because the stalls happen in the back end. You get a data cache miss, you get an L2 cache miss, the back end stalls, but there's no reason to stop the front end, right? If the front end is actually predicting branches and fetching instructions, you could keep running that loop as long as you decouple the back end and the front end with a huge queue of instructions. Right? Front end can be feeding the queue with instructions, back end maybe getting things out of the queue until it stalls completely. So that's the idea of fetch-directed instruction prefetching, basically. Instructions executed by a program is essentially a series of consecutive cache block addresses sequentially, followed by a gap, and this gap is created by branch instructions. And the instruction stream kind of looks like this, basically, if you're following this path, right? So the idea is to direct the prefetcher by predicting branches among prefetched instructions. Branch predictor directed instruction prefetching maybe is also another term for this. So essentially, you're accessing the current instruction, you start prefetching sequentially. And if you decode instructions such that you find the branch instructions, if you find the branch instruction, predict the target address of the branch, and basically start prefetching from that address. And you keep doing this repeatedly. It's essentially how you fetch instructions, except you need to decouple the front end and the back end if you don't want to stall. So the basic idea is the fetch engine can run far ahead of where in the program the execution units are currently executed. And I already said this, effectively decoupling the fetch engine from the rest of the pipeline. So a fetch engine runs ahead, generates instruction addresses, and puts them in a buffer called the fetch target queue in this original paper. And then the decode stage consumes entries from the fetch target queue and processes. And if your fetch target queue is huge, that's great. You could keep prefetching a lot of things, right? At some point, you may need to flush the fetch target queue if your branch is incorrectly predicted. And here the instruction prefetcher's benefits are dependent on the branch predictor's accuracy, right? Okay, this is a picture from one of the papers. People have improved on this idea to make this priority directed, etc. I will not go into those details, but essentially this is the fetch target queue. And you keep fetching instructions. It generates addresses over here. So fetch target queue can be over here or over here. Here you have addresses. Here you will have data, either way. But I think you'll need to have queues in both places to be nice. Okay, this unit keeps on generating instruction addresses using the branch predictor, and you keep filling it, and you look up, and you fetch the instructions, and you prefetch from the lower cache levels if needed, if you don't find them in the iCache. And then you could keep the instructions in the fetch target queue, or you could keep it in another queue over here in the decode stage. Okay, and then there's branch resteering that happens, as you can see, if the branch turns out to be mispredicted. Okay, so this is one example. I don't want to go into the implementation details of it, but you have the idea. So this idea was originally proposed in a paper in 1999, which received the Test of Time Award in 2020. It's a nice paper. I'd recommend reading it. And this idea has been implemented in many processors. A lot of IBM processors have this fetch-directed instruction prefetching, and they were the first ones to actually implement it for a very long time. And these are some interesting papers that they have written on this topic. AMD actually started implementing it more recently, and Intel also implements it, but I guess I don't know why these papers are not there. Rahul made these slides, so we should ask Rahul. Okay, Samsung also has this nice paper. Okay, so it's good to think about fetch-directed instruction prefetching versus other instruction prefetchers. So if you have fetch-directed instruction prefetching, do you really need other instruction prefetchers? So FDIP, it's called, it uses existing branch prediction structures to generate instruction prefetchers. And with sufficient fetch target queue size and branch prediction accuracy, it turns out fetch-directed instruction prefetching subsumes benefits of dedicated instruction prefetchers. So there's been a lot of dedicated instruction prefetchers. Next 4 line. If you think about it, FDIP subsumes that, right? Mostly. So this is a paper that was written by ARM in 2020, where they analyzed a lot of instruction prefetchers that people have proposed. Next line. These are the names of different prefetchers. There's no prefetching, and there's a perfect prefetching whenever you actually access iCache, The instruction is always there. You never get an I-cache miss. And if your fetch target queue is small, you gain, and if TB is disabled, you gain significant benefits from instruction prefetchers, as you can see. Now, if you have a large fetch target queue, and if you enable FDP, even with no prefetching, no additional prefetching than FDIP, you already get a lot of benefits. And the additional prefetchers actually don't provide you any benefits. That's interesting, right? So the question is, are all of these ideas useless? That's kind of the ARM paper tried to hint at. Actually, what they hinted at was maybe we should be using better baselines, meaning FDIP should be always the baseline, and we should try to improve on that. It's good to read that paper, I think. I don't think they're useless because they propose some ideas that could be useful in some other context, but maybe they're not that great for instruction prefetching when FDIP, fetch-directed instruction prefetching, is enabled. Maybe there are some processors where you don't want fetch-directed instruction prefetching, and the cost of these prefetchers may be lower. So the argument was not a cost argument, it's more of a performance argument. Yes?
What is the y-axis? Is it end-to-end speed up? Because 30% end-to-end speed up due to instruction prefetching, it's quite large, right?
Yeah. I mean, yeah, you need to look at the paper for more detail. I think they used some instruction-heavy workloads. So it's not, I believe the workloads that they used have a lot of instruction cache misses. Yes, it's not 1,000 workloads where some of them are dominated by data cache misses. I think they selected the workloads, if I remember correctly. So that's not unreasonable in that case, right? 30%. Yeah. Good question. This is a short paper, so we'll add it to the homework also for the next homework, so you can review it. That's a good paper. I think it's a very interesting paper written by industry, saying maybe we should rethink how we do instruction prefetching research. It's good when industry sometimes does it, as opposed to rejecting papers in the back scenes, let's say. Okay, so there's a lot more on prefetching that we didn't cover in some earlier lectures. You can take a look, or you can ask questions, or you can read papers. We covered actually a lot, but there's more to cover. And I would still suggest, if you're interested, you can join the championship. This is also a good time to talk about impactful research. If you actually want to do impactful research, we talk about a lot of research ideas. It's a very forward-looking course. We're always looking for people who are really interested in doing something big. And all topics in computer architecture course and more are fair game for us, basically. We do a lot of research in computer architecture. Prefetching is actually very interesting. And also hardware, software, co-design, systems, security, bioinformatics. You didn't have a bioinformatics lecture yet, right? Okay, we should have that at some point. Acceleration, essentially. And we're always looking for bright and self-motivated students who have a passion for rigorously solving problems and who are willing to do proper justice to scientific exploration, evaluation, and also communication of it. These things take time, so it's important to do it right. And we cherish working with students from all over the world with diverse backgrounds. So we have a nice, open, and inclusive environment where we value creativity, hard work, free exploration. Ideas are important, collaboration, and rigor. So Nika developed a lot of ideas, for example, for her thesis. She's going to present that in a few months, hopefully. We can come to her defense, right? Okay, you've seen some of these, so you can learn more about these, more about us online and some of the projects also. We have newsletters where we cover some of the projects, and we should really release the last newsletter this year before going into the next year. Okay, you can see some people also. And these are some of the postdoc and PhD alumni. Rahul is not here, so he's at the top, as you can see. He's the last one, number 25 in PhD. And we have a bunch of postdoc alumni, which is not complete over here. And you can learn more about that as well, if you're interested. Okay, I will not go into this more. But if you're interested, definitely talk with us. You have an advantage because you're taking this course where you're exposed to a lot of research topics. Not everything, of course, because it's not possible to talk about everything in a single semester where the area is huge. Computer architecture today is actually a very exciting area. It's at the center of many things, at the center of a lot of innovations, right? I would argue that all of AI is built on computer architecture today. If the computer architecture wasn't there, people would not be able to execute those workloads And even then, they're having trouble executing those workflows today. So please, if you're interested, talk with us, do the readings and critical reviews. Clearly, you're taking some of our courses or you're following online. And there are many topic areas, and these are not really everything that we're interested in. In general, I tend to be very driven by new ideas. So if you have some new idea or new problem, I'm always open to listening to that. I don't have a dogmatic view of, oh, this problem is a lot more important. Of course, I have some views. This problem is a lot more important. But that doesn't mean that I'm not going to impose that view necessarily, because some other problems are also important. And over time, problems may change, right? So it's good to have an open mind in problems. So that's why we actually work on a lot of different things, because different problems actually evolve over time as well. And we also have a very limited list of thesis projects, I think, or bachelor's, master's, and semester projects that are included here. We don't get to update it a lot. So if you're interested in working in these areas, you'd better talk to us. You can also look at the thesis, but that may not be up to date always. And this is an application, especially for people who are online. But if you're taking this class, we know more about you, so you can talk to us. Okay, that brings me to the end of the Prefetcher lecture. Any questions? Okay, we still have time, so we need to switch to the other lecture. Let's see if I can do it. I need to stop sharing. Do you need to download it, or is it downloaded already?
Maybe already downloaded.
Oh, okay, multiprocessors. Okay, good. Oh, I did it, maybe.
Did you share your screen in Zoom?
Did I share screen? I think so. This is
Okay.
sharing, right? Yeah, take a look. Was it sharing? Are they moving?
Yeah.
Okay. Testing is important. Okay, that's good. Yeah. Okay, we're done with prefetching. Now we're going to switch to a more, let's say, processor-centric side of the course. But even with multiprocessors, we're going to talk a lot about memory. So this is a fun part of the course where we will cover a lot of processors. And these are some readings. How many people here know about Amdahl's law? Probably almost everyone. If not, you're going to learn today. And this is the original Amdahl paper. And there are some recommended readings that I would recommend also. These you can find online. We're going to talk about memory consistency sometime next week. This is a seminal paper by Lamport, only 2 pages also. And cache coherence, we're going to talk about. This is a seminal paper by Janak Patel and a student, Papa Marcos. So we're going to cover multiprocessors. So what are multiprocessors? So Mike Flynn, who was a pioneer in computer architecture and computer arithmetic, he wrote this paper in 1966, where he analyzed computing systems. He classified computing systems into 4 groups. SIST is basically what does an instruction operate on, how many elements, and how many instruction streams are you processing concurrently. Single instruction operates on a single data element. That's kind of like a scalar sequential instruction stream, basically a single core processor. SIMD is single instruction operates on multiple data elements. This is GPUs, for example, array processors and vector processors. If you've taken DDCA, you would know this well. MISD is multiple instructions operate on a single data element. If you don't know this, the systolic array processor is an example of this, streaming processor. And multiple instruction, multiple data, you have multiple instruction streams operating on multiple data elements, essentially multiprocessors or multi-thread processors. And there are examples of this we've covered in DDCA. I'd recommend you take a look at the lectures, SysD, SIMD, MISD, systolic arrays. Today, we're going to talk about MIMD, essentially. But before we get into it, why do we design parallel computers? So parallelism is doing multiple things at a time. That's a very general thing, right? It's not applicable to computers only. Like humans have parallelism also. I'm talking and walking at the same time, right? I'm talking and thinking. So there's parallelism that's going on clearly. And things could be instructions, operations, and tasks. So what is the goal of parallel computer? Why do we design multiple processors, let's say? Let's make it even more concrete. Instead of designing a single processor, why do we want more than one processor? Anybody? Yes.
To extract parallelism.
Okay, why?
such that we can execute things
Uh-huh.
make it faster.
Make it faster. Yes, performance basically. We want to improve performance faster in terms of either execution time or task throughput, right? Because if you actually partition your program into two and execute those two pieces in parallel, hopefully you improve performance by 2x, right? And if you partition your program into 4 and execute those 4 things in parallel, you improve performance by 4x. If you partition your program into 100 and execute those 100 pieces in parallel, hopefully you improve your performance by 100x, right? That sounds good. That's basically perfect parallelization. Somehow perfectly, when you parallelize your program, you divide the execution time with the original execution time. So if you execute your program on n processors, you divide the execution time on one processor by n. That's ideally what you would expect, right? Unfortunately, that's not always the case because of Amdahl's law, which we're going to see more, and you probably have seen it at some point in your life, because Amdahl's law says there's a parallelizable part of a program and there's a non-parallelizable part of a program. And when you actually execute a program on a multiprocessor or parallel processor, you improve the performance of the parallelizable program by n, divide that fraction by n, but the non-parallelizable fraction remains. So if your parallelizable fraction is 50%, and if you execute that on an infinite number of processors, that goes to 0, but your speed up is 2, because 50% of the program did not improve, right? That's the idea of an Amdahl's law, and that's very powerful, as you can see, right? So 50% is not a good parallelizable fraction, as you can see. Okay? So what about other goals? Are there other reasons to do parallelism? Is it just performance? Anybody? There's no other reason? Okay, yes.
Sometimes, so if you have only one single core, you might have to make many smart things to make that one thing go faster. But if the program is naturally parallelizable, you can have two slower cores, but still get better performance. So that is in general like saving resources to design for that one core, and you can just use two suboptimal cores and still get more benefits.
Okay. Okay, potentially yes. I would say that you're getting into more resource efficiency or energy efficiency. I'll take it. I'll say power consumption, let's say, because a single core, essentially, a single core, you may need to use techniques like, let's say, frequency. I like the frequency because it's a very concrete. Let's say you have a single core, and you need to increase its frequency a lot to get a good performance. But if you have a parallelizable program, as you said, maybe you have 4 cores and make each of those frequency f divided by 4. Now it saves you power consumption and also a design complexity, because you don't need to design a core that is 4 times the frequency. But let's take a look at the power consumption. Essentially, 4 units at frequency f over core consumes less power than 1 unit at frequency f. Do you buy the statement? I buy it, of course. That's why it's here. And I ask you why. Why is this true? Automatic, that's good. Now I have to figure out how to write. Okay. Can people see it? Or maybe you can try it. So basically, you have 1 unit. This is frequency f. And you have 4 units. Each of them is frequency f over 4. I contend that this is much higher power. This is the power 1. This is the power, or let's say power is serial, single processor, and power parallel processors. I would argue that PP, the power parallel processor, is much lower than power single processor. Anybody agree or disagree? Okay. No? Genome agrees, I think, but he's too shy to talk. Okay, so basically, the assumption is perfect parallelization, right? I perfectly parallelize my program such that I can execute it at the same time. So what is power? Power is normally some activity factor times CV squared times frequency. That's dynamic power. This is the dynamic power equation, which you may have seen in DDCA lecture 2 or so, right? 2 or 3, I don't remember, 2 probably. And basically, now let's take a look at what is CV squared F over here. For this large processor, clearly this is F, and this is VS squared, and this is CS, and there's some activity factor. Let's ignore the activity factor for now. Let's assume these are all active the same amount of time. They're doing the same amount of work for some reason. That will complicate things. So this is PS, and this is PP equals, ignoring the activity factor, this is capacitance of P, voltage of P squared, and this is F over 4. So clearly we have F over 4. Right? So this wins, assuming CP and VP are equal to CS and VS. Now let's take a look at VP versus VS. Now, if you want to get a high frequency in a machine, you'd better have very high supply voltage so that you can switch things much more quickly. And it turns out voltage and frequency are correlated. So this voltage is actually correlated. I don't want to use alpha again. I'm a beta frequency. And here, you don't need that much frequency, so you can actually reduce the voltage a lot. So this is a beta F over 4 squared. I mean, maybe you square the beta also, doesn't matter. That's not our point over here. Does that make sense? So this voltage is proportional to the frequency. So if you reduce the frequency by 4, you reduce the voltage by 4 also. And the power equation is quadratic with voltage. So you get a 16x decrease in the power because of voltage and 4x decrease in power because of frequency. And now you get a 64x decrease in power compared to power of the single processor. Now the question is, what is capacitance? That's a bit harder, of course, to analyze. But again, this capacitance is based on the loading that you have in the circuits. In general, to support a higher frequency, you usually need to have something high capacitance. So I don't know what the exact equation is over there, which is very hard to determine in the exact circuit. So this here you gain in capacitance also, but even if you ignore the gains in the capacitance, you're much more power efficient here, right? Does that sound good? Hopefully this makes sense. So with these assumptions, if you can parallelize your program perfectly and run it at the same time, you're saving a lot of dynamic power by parallelizing your program. Okay? So that's the idea. So that's the power consumption angle. And this is very useful. And this is the reason why people moved from single core. Well, it's not the only reason, but this is one of the reasons why people moved from single core to multi-core, because making the frequency and the performance of this higher and higher was becoming very power hungry. If you could actually go into something like this, you could become less power hungry. The downside is, of course, when the assumption doesn't hold, right? If your assumption of perfect parallelization doesn't hold, then you're losing performance, you're executing for longer. And as a result, yes, this is true, but because you're executing for longer, you're also consuming more power. And activity factor may be increasing, etc. So there may be actually a lot of things that are happening. Still, 64x is pretty, if your goal is just energy, 64x is pretty hard to overcome. If you execute for longer, now your static energy. This is the dynamic power. There's also static power, which is essentially correlated with temperature and also your area and also time, how long you execute. Your static power increases if you're executing longer over here. Okay, and again, I'm not going to static power, but that's the idea. Okay, how do we get back? Somebody knows? Okay, and you prefetch him? Okay, so while you're doing that, what else? So that was another reason. We talked about performance, power under some assumptions. What other reasons are there? Yes.
If we assume that we have the same area
Mhm.
for one core or multiple smaller cores, it's easier to manufacture. Somewhere you could just say, well, one small core instead of
Yeah.
throwing away the whole.
Yeah. Okay. You combine multiple concepts over here. I don't know which one to get at. So you're saying you would save area with a parallel processor?
No, I'm saying cost.
Cost. Okay, yeah, I think that's the last point. I cannot do out-of-order execution on the slide. Cost and scalability. Yes. Basically, one single core is much more complex, and you can have much smaller cores that are actually much more scalable. And again, less costly because one of them is more costly to design to get the same performance. If you actually have smaller things, it's a lot easier to design. Yes. So that goes into cost and scalability. What else? Yes.
Moore's law is now becoming a bit slow, so we might be getting at some limit as to how much you can actually optimize with just one CPU. But you essentially don't have any hard limit with how much you can optimize with multiple cores, provided your program is that much
Yeah. I don't know. I think that goes back to the cost issue, right? A small core is less costly and more scalable. So maybe you're saying the same thing. I'm looking for something fundamentally different. Yes.
In the main goal, you're talking about execution time of one program, but maybe you want to run multiple things at a time, which is the concept of parallelism.
Well, that's the task throughput, basically. Yeah, that's essentially you have a throughput. Yeah, if you're running many things, your task throughput increases. Yeah, good try, but yeah, it's already there. I want some fundamentally different goal. Forget about performance. Forget about energy. Forget about cost and scalability. We've covered something else that's important in this lecture, in this course, not in this lecture yet. Yeah. Should I say it, or are you guys gonna, someone's gonna blurt it out? What's important? If the core doesn't work, if you have one core and it doesn't work. Exactly. Yeah. Well, I guess it's at the end. Sorry, I forgot the order. So we covered the cost, improving dependability, basically, robustness, right? So if you have a single core and it doesn't work, it doesn't work. But if you have 10 cores and if one of them doesn't work, who cares? In fact, if 4 of them doesn't work, who cares? If 5 of them doesn't work, okay, now you may be in trouble. Depends on how they don't work. If 5 of them gave you answer A and the other 5 gave you answer B, you're in trouble, right? So basically improves dependability, right? As you can see, because it enables you to redundantly execute a program in space, meaning in different spaces concurrently, so that you can select the most popular answer, hoping that the most popular answer is the correct answer, right? That's the idea. Okay, good. Are there any other reasons? You can think about it. I covered a lot of things over here: cost efficiency, scalability, complexity, because they're all related, basically. It's hard, essentially, as we discussed, it's harder to design a single unit that performs as well as n simpler units. The assumption is that the program is perfectly parallelizable. Okay, so people have done a lot of parallelism exploitation, and there are many different types of parallelism: instruction level parallelism, data parallelism, and task level parallelism. Instruction level parallelism, we've done this a lot in digital design and computer architecture, for example. Different instructions within a stream can be executed in parallel: pipelining, out-of-order execution, speculative execution, VLIW, data flow. They're all instruction level parallelism. You try to parallelize different instructions. Data parallelism is fundamentally different because you may be doing the same operation on many different data levels. Essentially, different pieces of data can be operated in parallel. And this is essentially the core of SIMD, single instruction multiple data processing, vector processing or array processing, or systolic arrays are also a part of this, GPUs, clearly. Essentially, you're doing a vector addition operation, for example. You're multiplying two matrices. You're essentially doing the same operations on many data elements. And this is clearly good for exploiting parallelism, and we have architectures that are designed for this. Now, task-level parallelism is at a coarser granularity. Different tasks or threads can be executed in parallel. They may have something to do with each other, or they may have nothing to do with each other, like the throughput of different tasks, different programs. And this is exploited using multi-threading or multiprocessing. And one form of multiprocessing is multi-core, clearly. So the task-level parallelism, how do you actually create these tasks? One is run many independent tasks or processes together. That could be relatively easy. The harder part, which we're going to examine a lot, is how do you partition a single problem into multiple related tasks or threads? You could do this explicitly by doing parallel programming. And this is easy when tasks are natural in the problem. For example, you have a database and there are lots of queries coming. They still share some resources potentially, but then it's difficult when natural task boundaries are unclear. You have a problem you now want to solve and you want to partition that problem. It may not be clear what are the task boundaries. Or you can do this transparently or implicitly. Now this becomes similarly to what we discussed earlier, speculative threads, except you're not doing this just for prefetching, but you're doing this to execute the program. You can basically take a single threaded program and speculatively partition it, execute it on different processors, and try to preserve the results. Assuming your partitioning was accurate, and maybe you predicted the values correctly, and orchestrate the computation nicely, you automatically parallelize the program on multiple different processors. This is called thread-level speculation. It's much harder to do, but people have looked at this a lot also. Okay, I will not go through this in detail right now, but we're going to look at some examples of it in the next few lectures for different things. The second way of getting tasks or creating tasks is running many independent tasks or processes together. And here, this is easy when there are many processes. For example, you have a cluster and people submit batch simulations and everybody submits a different job, or you want to actually simulate a million different configurations of the next processor you're designing, and you're running your simulator. All instances are independent of each other. As a result, you have a lot of parallelism, right? Different users may be submitting jobs. Cloud computing is a perfect example of running many processes together on a multiprocessor. Now, the downside of this is it doesn't improve the performance of a single task, because that's not the goal. Because single task, you could still improve, you could still parallelize it, but the goal of this running many independent tasks together is exploit a different level of task-level parallelism. So we'll cover some fundamentals before we get into difficult issues. So difficult issues really happen. I mean, running many independent tasks we've seen in this in these lectures, for example, when you actually run independent tasks and they share resources, clearly there's a lot of interference that happens. And we talked about interference issues. That's one issue. But there are other issues that happen when you partition a single problem into multiple related tasks. Let me go into a little bit fundamentals before we go into the deeper issues. So when you design a multiprocessor, there are actually only two major types: loosely coupled and tightly coupled. And they differ in terms of how they expose the memory space to the processors. Essentially, in a loosely coupled multiprocessors, there is no shared global memory address space across the processors. Processor 1 has its own memory address space. Processor 2 has its own memory address space. Processor 3 has its own. And processor 1 cannot directly access processor 2's memory address space. It cannot say load from this location, and that location belongs to some other processor. That is not allowed because they don't share a global memory address space. Tightly coupled multiprocessors share a global memory address space. All processors see the same memory, and they can do loads and stores. They don't have a partitioned memory from the software perspective. In the hardware, everything can be partitioned, but from the software perspective, in the software, you cannot say, you can easily say basically load from location X, and another processor can say load from location X, and those two locations are the same essentially. Right? And this clearly defines the programming model also. So a multi-computer network is essentially a loosely coupled multiprocessor. Like right now, this laptop and that laptop, they're all loosely coupled multiprocessors. I can distribute a task on top of them as long as I have the permissions to do so, right? Of course, you can have another multi-computer network in a data center, for example, without a global shared memory address space. These are network-based multiprocessors, essentially. Whereas traditional multiprocessing is actually tightly coupled. This is also called symmetric multiprocessing. People don't use that term a lot these days, but essentially existing multi-core processors or multi-threaded processors, they're all tightly coupled, meaning they share a global memory address space. You can write different threads, and you can do load from location X in one thread and store into location X another thread, and they conflict with each other or they communicate with each other. Okay, so usually the loosely coupled multiprocessors are programmed via message passing at the high level. What does this mean? Basically, because you cannot say load from location X and store from location into location X across different threads, you need to explicitly send and receive messages. Right? That's how the internet operates, actually. Internet is a network. So you need to actually say, okay, send this message to this process, or receive this message from this process. So there needs to be explicit calls for communication across processes. So the programmer needs to handle it this way, which may be hard, which may be easy, depending on how you're trained. But certainly it's different from how you can do tightly coupled multiprocessing with shared memory address space. Essentially, programming model of tightly coupled multiprocessors is very similar to uniprocessors, meaning load store, except operations on shared data require some sort of synchronization, because one thread can load from a location that another thread writes into or stores into. But essentially, you can think of all of the operations happening on the same memory, right? There is no explicit send or receive across processes. It's always loads and stores. So very similar to a single threaded program, except you have multiple threads that are communicating with each other through loads and stores to the same shared memory locations. Right? So to handle conflicts, you need to synchronize operations that happen on shared data. Make sense? So probably you're used to programming things like this. Is that correct? Have people done parallel programming classes? Who has done, I guess? And you've done this sort of programming in general? Has anyone done this other sort of programming? Okay, you've done both in the parallel programming? I guess you could do it parallel programming, that's true. So yeah. Which one's easier? No thoughts? Depends on the problem. Okay, good. I agree with it depends on the problem. It also depends on the person, what you're used to, potentially. Okay. So there are many, we're going to talk a lot about tightly coupled multiprocessors, but a lot of things apply to loosely coupled as well. And yeah, these things can be combined too. Essentially, there are many design issues in tightly coupled multiprocessors. One is shared memory synchronization, how to handle synchronization, locks, atomic operations, barriers. We're going to talk about some of these, but we're not going to talk about the software perspective. For that, you need to take a parallel programming course. We're going to talk more about how to handle these from the hardware side a little bit, not completely, because we don't have a lot of lectures. Cache coherence, how do you ensure correct operation in the presence of private caches, keeping the same memory address cached, which is going to be important for the programmer especially. Memory consistency, what kind of ordering does the programmer expect the hardware to provide? Ordering of all memory operations. We've already covered shared resource management in some earlier lectures, and we're not going to talk as much about that in these lectures. And we're hopefully going to cover an important aspect of communication across these processors. How do you connect these processors together? And what kind of structures do you use to connect them? What kind of routing mechanisms do you use, etc.? So that's going to be important, and we're going to talk about interconnects. So these are some of the main programming issues in tightly coupled or shared memory multiprocessors. Load imbalance is something that we're going to discuss a lot. How do you partition a single task into multiple tasks such that processors have equal amount of work? Because if they don't have equal amount of work, you're not using your processing system efficiently. And we're going to talk about that. Synchronization, we're going to talk about how do you synchronize efficiently between tasks? How do you communicate between tasks? We're going to look at different types of things, maybe not all of these, but we're going to talk about how to handle this in hardware. I think contention, avoidance, and management, we discussed that, but we're going to look at it from the perspective of coherence a little bit. How do you maximize parallelism? And how do you ensure correct operation while optimizing for performance? And this is the most difficult part, basically. You want to get high performance, and usually there's a trade-off between high performance versus correctness. You can always get high performance by being not correct. And it's very easy to be not correct when you're doing multiprocessing, because you may actually forget or incorrectly synchronize threads. You may forget something, right? I don't know if you done that when you did parallel programming. If you're taking an operating system course and if you're writing, for example, synchronization primitives, you have to get that correct also, for example, so that somebody else gets the usage of those synchronization primitives correct. Okay, so there's an aside, which is hardware-based multi-threading, which is essentially similar to tightly coupled multiprocessing, but there are also multiple types of multi-threading. One is coarse-grained. Essentially, you switch between different threads on the same context, hardware context, or quantum-based essentially, or event-based. Quantum-based is basically every time there's some time quantum, a thread executes, after its quantum expires, another thread comes in, right? Or it could be event-based, switch on event. For example, when there's a long latency cache miss, you switch to another thread. These are potentially independent threads from the same program or some other program. Fine-grained means every cycle you switch to another thread. So this is actually an interesting idea to make the design of a pipeline simple. This increases the throughput of the pipeline because you don't need to deal with data dependencies or branch predictions. Every cycle you fetch from a different thread, such that you don't need to predict branches, or you don't need to handle data dependencies. And this is employed in many systems, including modern GPUs. Simultaneous is the most aggressive form. You can basically dispatch instructions from multiple threads at the same time in out-of-order execution units and superscalar processors. This way, you can actually improve execution unit utilization. This is what Intel called hyper-threading, for example, instead of simultaneous multi-threading. So these are different kind of hardware-based multi-threading. And all of the issues that we discussed for tightly coupled multiprocessing actually apply to hardware-based multi-threading also. Because multi-threading requires multiple threads, and they're executing actually on the same core with multiple contexts in this case. And everything that we're going to discuss is going to apply. Makes sense, hopefully. Okay, if you want to brush up on fine-grained multi-threading, we have a lecture on that. And there's a lot more lectures on multi-threading that we're not going to cover, unfortunately, because we don't have time. Okay. Okay, let's see how much time we have. Okay, let's start, and maybe I will give you the problem and you can have ChatGPT solve it. Actually, it's a good problem to test ChatGPT on. First of all, it should be able to read my writing. I don't know if it's possible yet. Okay, so basically, this is a parallel speedup example. I guess it can read this one. This is a polynomial, as you can see. X is an input, and AI is essentially some constant. And we're going to compute this polynomial's value. Right? You're going to assume some given inputs, x, and each AI. Right? It's a4 x to the power of 4 plus a3 x to the power of 3, a2 x to the power of 2, plus a1 x plus a0. So assume each operation is one cycle. There is no communication cost whatsoever across processors, across instructions, etc. Each operation can be executed in a different processor. So some ideal assumptions. The question, there are multiple questions basically. How fast is this with a single processor? How fast can you execute this code? So one instruction can do multiplication, another instruction can do addition. Okay? Assume no pipelining or concurrent instructions. Basically, each addition takes one cycle and one cycle. Because it's a single processor, there's no concurrent execution. And then the next question is, how fast is this with 3 processors? Nope. Okay. Maybe we can give you some time. Do you have enough time to input this to ChatGPT? Maybe someone can do this in the background. I'm curious what it will barf. Anybody? Okay, let's do the single processor. You can calculate using a paper or your head. Any guesses? Or not? Or maybe it's too late on a Friday to calculate. The first one is easy with a single processor because you can only execute one operation on the single processor. And you clearly need to serialize all of these. Anybody? Maybe I'll give you the one processor. This is the one processor version. It takes actually 11 operations. And because each operation is a single cycle, it's 11 cycles. And basically, I drew the data flow graph over here, right? So you can see that we multiply x. This is the multiplication part. And this is the other multiplication part. And this is the addition tree or graph. So this is x squared over here. This is x cubed. This is x to the power of 4. And now a4 times x to the power of 4 right here. And this is a3 times x to the power of 3. You add those again. a2 times x to the power of 2. a1 times x to the power of 1. And you keep adding those. And eventually you add a0. And that's the result. So this is really the data flow graph. Is this the best you can do? With these assumptions, I would argue yes, unless you have a different assumption. Yeah. What about 3 processors? Challenging you on a Friday evening. Okay, this is the solution with 3 processors. It's a bit more complicated.
Actually, it said 8. 11 was correct, but this one, it said 8.
Okay.
So this one, it did it correctly.
It didn't do this one correctly.
It said 8.
Maybe I'm wrong. It said 8 to this one? Are you sure you prompted it right?
I sent the screenshot of the slide. Your first slide with the questions.
Okay, look, this one.
Yeah.
Oh, okay. And then it actually calculated. Okay, good. Okay, so this is the solution with 3 processors. It's 5 cycles. The question, basically, then you can compute the speed up, right? Speed up with 3 processors is 2.2. The question is, this is a fair comparison. So you have 3 processors, you get a 2.2x speed up. Not bad. What am I getting at? Is this, so basically the question you want to ask to yourself is this the best program I can design for a single processor? And is this the best program I can design for a multiprocessor with 3 processors? ChatGPT is stupid. Sorry, I had to do that because it got both of them wrong. I don't know how it got 5. Oh, 8, I don't know how it got 8, basically. But I can see that because 8 is possible to get if you don't optimize this graph. Ask ChatGPT to optimize the first one. Because this is a terrible solution. Can anybody guess why? This is actually the optimal solution for 3 processors. This is a terrible solution. Tell ChatGPT it's a terrible solution. Can you can you use some mathematical principles that are out there from 1800s and fix this? Okay, so why is it a terrible solution? Because it's not optimized essentially. So you can revisit the single processor algorithm. How many people know the Horner's method here? Have you ever used it in high school? There you go. This is where things become important. Those mathematical things that you thought you would never use become important when you optimize programs. And ChatGPT, ask ChatGPT to use Horner's method to optimize. Okay, maybe if ChatGPT couldn't figure it out on its own, use Horner's method to actually try to optimize this. Okay, if you use Horner's method, which you may have learned, there's a beautiful paper about it. Essentially, you do this. You factor the polynomial in a different way, as opposed to the, let's say, maybe what you would think of immediately. That's why ChatGPT gives you 11 cycles. You refactor the polynomial this way, starting basically taking x out with every iteration. You have seen another version of Horner's method, which I have seen another version actually, but this is actually the polynomial expression. And if you do it this way, now you have much fewer operations, right? This is what you have. So this is a4x, add to it a3, and then multiplied by x, add to it a2, multiplied by x again, add to it a1, multiplied by x again, and add to it a0. And that's the result. And that's essentially what we have over here. Makes sense, right? And that's only 8 operations, which is 8 cycles in a single processor. And 8 divided by 5 is 1.6, which is much smaller than 2.2. So because we didn't use the best program, that's best known algorithm to compute this polynomial, we originally overestimated the speed up. And I don't know what ChatGPT did, but it did 11 divided by 8, which makes no sense. Neither of them is best, basically. Okay. Does that make sense? So basically, the point is, you need to be very careful when you're comparing performance of processors. Even with these very simplistic assumptions, you can get it wrong because you may not use the right algorithm. For fair comparisons, you should use optimized algorithms for both types of systems. And the algorithms that you use for a single processor versus a multiprocessor is different in the end, in most cases. Actually, in all cases, almost. Because a parallel algorithm is very different from a sequential algorithm in the end. Okay, so there's also, because you may not do the fair comparison, you may actually get superlinear speed up. And this is actually a fascinating and funny area because people have reported you have P processors and you get more than P improvement in performance compared to a single processor. So normally that should not happen. Typically you should get, as you increase the number of processors, you should get not at most linear speed up. Right? But usually you get less than linear speed up because of Amdahl's law. And we're going to see more and more issues with Amdahl's law. Not Amdahl's law, but parallelization. You've already seen interference issues, but because of resource interference, you may not be linear. Right? So one of the reasons why you would get superlinear is unfair comparisons. You need to be very careful. You need to compare best parallel algorithm to wimpy serial algorithm. And if you do that, you get unfair. But sometimes you can actually get cache and memory effects that lead to superlinear speed up. Because when you actually add processors, you're also adding cache or memory. And at some point, with a single processor, you have X amount of cache. With n processors, you have n times X amount of cache. And with a single processor, you're always going to memory. With n times X amount of cache, that's enough to keep your data set, for example, in the processors. And you're never going to memory. And that could actually get you superlinear speed up. Right? Is this a fair comparison, unfair comparison? It's a bit hard to tell depending on what you're looking for. The number is correct, certainly, even if you, basically you're assuming that you're using the best algorithm for both. But the reason you're getting superlinear speed up is not coming from the fact that you're adding more processors. It's really coming from the fact that you're adding more memory or cache. So it's good to consider this. And this is actually real. Even if you're using the best algorithm, you're not unfair because algorithmically, you may be getting superlinear speed up. So there are good reasons why you may be getting superlinear speed up also. But in our problem, it was not the case, right? There's no cache, there's no memory. We ignored a lot of those issues. Okay, I think this is a good place to stop because it's already late. We're going to pick up the next week from here. So hopefully this was interesting. It gives you some things to think about in fair comparisons and multiprocessing. And then we're going to continue and look at a lot of interesting issues in multiprocessing starting next week. Have a great weekend. I'll see you all next week. Did ChatGPT respond?